Hi everyone and welcome to this course. My name is Martin Yanev, a professional software engineer and a computer science professor at Fitchburg State University. Today I'm going to show you the most popular and widely used Java design patterns. We're also going to cover object-oriented programming principles like abstraction, polymorphism, inheritance, encapsulation, and many more. We will explore how those concepts, along with the solid principles, can drastically improve and scale your code. The course is full of code examples and you can find all of them in our Git repository linked in the description. This course is going to be about 4 hours, so take your time to go through it. I would really advise you to watch the complete course. Even if you put it on the background while doing something else, it's still going to give you a lot of knowledge. Now, if you feel that what you see today is valuable for you, please like this video and subscribe the channel for more similar free content like this one. Now, let's get started.
Every software architect or developer often faces the challenges of structuring code, how to develop a code structure that remains sustainable, just as an artist draws their painting. Today, we're diving into the fascinating world of software design patterns, an essential toolkit for any coder wishing to create elegant and maintainable software. Now let's see how we can implement a simple vehicle class that embodies the principle of encapsulation. In this class, we have a private Boolean attribute named moving, which indicates whether the vehicle is in motion. By making moving private, we ensure that its state cannot be altered directly from outside the class, thereby protecting the integrity of the vehicle's status. Next, we provide two public methods, move and stop. These methods serve as controlled access points to modify the internal state of moving. When the move method is called, it sets moving to true and provides feedback to the user that the vehicle has started moving. Conversely, calling the stop method sets moving to false and informs the user that the vehicle has stopped. Finally, we also include a method named isMoving, which allows external classes to check the state of the vehicle without modifying it. This structure not only promotes a clear interface for users of the vehicle class, but also exemplifies encapsulation by keeping internal details hidden while providing necessary functionality. Through this class design, we see how encapsulation helps maintain control over the object's state, enhancing robustness and maintainability. Now let's take a look at how we can define an interface called movable. This interface declares a method move, which is intended to be implemented by any class that wants to define specific movement behavior. This is a crucial step in achieving abstraction because it allows us to establish a contract that all implementing classes must follow, ensuring consistency in interaction while allowing for diverse implementations. Next, we will create specific classes that implement this movable interface. For instance, the bicycle class implements movable and defines how a bicycle moves by overriding the move method. Inside this method, we detail that when a bicycle moves, it outputs a message stating bicycle is pedaling forward. Similarly, we have the car class, which also implements the movable interface but sets its own behavior for movement, stating car speeds down the road. This structure exemplifies how different types of vehicles can share a common interface with unique behaviors, thereby enhancing flexibility and reducing complexity in our code. Should we decide to introduce a new type of vehicle in the future, we simply need to implement the movable interface, showcasing the power of abstraction in our design. Now let's take a look at how we can implement inheritance in our code. We begin with a base class called vehicle, which contains a method named describe. This method is intended to provide a general description of what a vehicle is. By creating this base class, we establish a foundation that captures the shared characteristics of all vehicles. Next, we extend the vehicle class to create more specific types of vehicles, car and truck. Both subclasses inherit the properties and methods from vehicle, which means they have access to the describe method. However, they also have the capability to override it, allowing each subclass to define its own unique behavior. For instance, when we call describe on an instance of car, it prints a message specific to cars, while an instance of truck does the same for trucks. This demonstrates how inheritance not only facilitates code reuse, but also promotes flexibility, enabling us to introduce new vehicle types with minimal redundancy, thereby highlighting the hierarchy and structure of our code effectively. Now let's see how we can implement a function that utilizes our movable interface. We start with a static method named testMovement, which takes a movable object as a parameter. This method invokes the move method on the passed object, demonstrating polymorphism, allowing different types of objects to be treated uniformly based on their shared interface. In the main method, we create instances of bicycle and car, both of which implement the movable interface. Each instance is assigned to a variable of type movable, showcasing the flexibility of our design. By calling test movement with my bicycle and my car, we trigger their specific move implementations, resulting in unique outputs reflecting their behaviors. Bicycle is pedaling forward for the bicycle and car speeds down the road for the car. This example illustrates how polymorphism enables us to extend our code effortlessly. If we wanted to add another vehicle, say a bus, we simply need to implement the movable interface, and it would work seamlessly with the test movement function without altering any existing logic. This is a powerful feature of object-oriented design, providing both flexibility and maintainability. Next, we will explore the implementation of the Singleton pattern through a practical example. In our code, we define a class called database connection that is constructed to ensure only one instance of itself is created throughout the application. This is crucial in scenarios like managing database connections, where having multiple instances could lead to unnecessary resource consumption and potential conflicts. The key feature of the Singleton pattern is the private constructor, which prevents any external classes from directly instantiating the database connection class. Instead, we provide a static method called getInstance. This method is responsible for checking whether an instance of database connection already exists. If it does not exist, it creates one, effectively controlling the instantiation process. This implementation ensures that any call to getInstance will return the same instance, thus maintaining consistent access to the database connection throughout the application. Through this design, we can efficiently manage resources and establish a global access point to the database connection, embodying one of the core principles of the Singleton pattern. Next, we will explore the adapter pattern through a practical code example that allows us to integrate two incompatible interfaces seamlessly. To facilitate this, we define an interface called engine, which mandates that any class implementing it must provide a start method. We start by creating a class named SimpleEngine, which adheres to this interface and simply outputs a message when the start method is invoked. However, to incorporate the V8 engine, which has a different method called ignite, we cannot modify the existing car class that relies on engine. This is where the adapter pattern shines. Now let's implement the V8 engine adapter, which implements the engine interface. In its constructor, this adapter takes an instance of the V8 engine. When the start method is called on the adapter, it translates the call by invoking the ignite method on the V8 engine. By using this adapter, we can adapt the functionality of an incompatible class to work with existing code. This approach enhances flexibility and reusability, allowing the car class to utilize both engine types without requiring alterations to its design. Now let's implement an example of the observer pattern, which enables one-to-many communication between a subject and its observers. In this code, we create a weather station class that holds a list of observers. It provides a method to add an observer, allowing multiple objects to register their interest in weather updates. Next, we define an observer interface that mandates an update method. This is crucial as it sets the standard for how observers must respond to state changes in the subject. Then we introduce a phone display class that implements the observer interface, providing a concrete implementation of the update method, which simulates how a phone display would react to new weather data. With this structure, the weather station can notify all registered observers whenever there's a change in weather conditions. This pattern is particularly useful in applications where multiple components need to react simultaneously to changes in state, fostering a clear and organized approach to managing such interactions. Overall, this code exemplifies how the observer pattern promotes loose coupling between classes, enhancing maintainability and scalability in software design. As we draw this journey into software design patterns to a close, remember that understanding these concepts is not just about writing better code. It's about constructing a mindset that embraces clarity, predictability, and simplicity in software development. Each design pattern is a tool, and like a well-equipped craftsman, knowing which tool to use for a specific job will enable you to build robust and maintainable software systems. So next time you sit down to write code, think about the patterns you can apply. Design your software like an artist, creating not just functional pieces, but timeless works of art that can be understood and appreciated over time. Happy coding. Object-oriented programming principles form the backbone of effective software design. They enable developers to create structured, maintainable, and efficient code. Today, we will explore these principles in depth with a focus on Java, a language that embodies these concepts beautifully. So far, we have learned about the importance of structuring code sustainably and the role of design patterns in achieving maintainability in software development. We explored key principles of object-oriented programming, including encapsulation, abstraction, inheritance, and polymorphism, which aid in organizing and reducing complexity. Additionally, we discussed the three main types of design patterns: creational, structural, and behavioral, and how they can be applied to create flexible and reusable code. Ultimately, understanding these concepts fosters a mindset that values clarity and simplicity in software development. Now we will talk about the core principles of object-oriented programming. Now let's take a look at the bank account class, which demonstrates how encapsulation can be effectively utilized in Java. The balance variable is declared private, ensuring that it cannot be accessed directly from outside the class. This is crucial for maintaining the integrity of the account, as unintended modifications can lead to inconsistencies. Next, we implement a constructor that allows the user to initialize the account with a specific balance. This sets the starting point for financial transactions. To interact with the account, we provide three public methods: deposit, withdraw, and get balance. The deposit method checks if the amount to be added is positive before updating the balance, thereby avoiding any negative deposits that could violate the account's integrity. Similarly, in the withdraw method, we validate the withdrawal request to ensure that it doesn't exceed the current balance or request a negative amount. This safeguard is essential for preventing overdrafts. Lastly, the get balance method allows users to retrieve the current balance without exposing the balance variable directly. This encapsulation approach not only protects the data, but also promotes organized and maintainable code. Now let's see how we can implement abstraction in Java using an interface. Here, we create an animal interface that defines the behaviors eat and sleep. This interface acts as a contract that any class implementing it must fulfill, ensuring that both dog and cat provide their own specific implementations of these methods. Next, we will see the classes dog and cat that implement the animal interface. Each class overrides the methods eat and sleep, providing unique behaviors for each animal. For example, when we call the eat method on a dog object, it will output dog is eating, while a cat will output cat is eating. This design allows us to interact with different animal types through the common animal interface, reducing complexity and enhancing code maintainability. If we decide to introduce a new animal, such as a bird, we can simply implement the animal interface without modifying existing code, demonstrating the flexibility and power of abstraction in object-oriented programming. Thus, we maintain a clean and organized structure, making our codebase easier to expand and manage. Now let's take a look at how inheritance works in Java. In our example, we start with a vehicle class that has a method called start. This method simply prints a message indicating that the vehicle is starting. By defining this method in the vehicle class, we establish a base functionality that other classes can use. Next, we create two subclasses, car and truck. Both of these classes extend the vehicle class, meaning they inherit the start method. This is a key feature of inheritance. It allows us to reuse code and promote a clean structure. For instance, both the car and truck can start in the same way by calling the inherited start method without duplicating code. However, each subclass also has its unique characteristics. The car class adds a method called honk, which prints a message that the car is honking, while the truck class introduces a method called load that indicates the truck is loading cargo. This demonstrates how inheritance enables us to maintain a common interface while allowing specific behaviors. By leveraging these features, we reduce redundancy and make our code more organized and maintainable. Now let's take a look at how we can implement polymorphism in Java. We start by defining a base class called shape, which includes a method named draw. This method serves as a general blueprint for how different shapes should be drawn, providing a default implementation that simply outputs drawing a shape. Next, we have two classes, circle and square, that extend the shape class. Each of these subclasses overrides the draw method to provide their specific implementations. When we call draw on a circle object, it will output drawing a circle, while calling draw on a square object will yield drawing a square. This showcases polymorphism, as we can treat both circle and square objects as instances of the shape class, yet they behave differently when the method is called. In the main class, we declare a reference variable myShape of type shape. By assigning a circle or square object to this reference, we leverage polymorphism, allowing us to invoke the appropriate draw method dynamically at runtime based on the actual object type. This flexibility greatly enhances our code adaptability and illustrates one of the key advantages of object-oriented programming. Now let's take a look at how we can implement classes for product, order, and customer in our e-commerce platform to adhere to object-oriented principles. We begin with the product class, which encapsulates two private attributes, name and price. This encapsulation ensures that these properties are protected from direct access, promoting data integrity. The constructor initializes these attributes, while public methods allow access to their values through getter methods, enabling controlled retrieval of product details. Next, we define the order class, which maintains a private list of product instances. This class is responsible for managing the order's lifecycle, including adding products and calculating the total order amount. The addProduct method updates the products list and provides feedback when a product is added. Importantly, the calculateTotal method leverages streams to compute the overall cost efficiently. Finally, we implement the customer class, which has a private name attribute. This class encapsulates the action of placing an order, utilizing the placeOrder method to calculate and display the total amount of the order. Each of these classes illustrates clear responsibility and modular design, laying the groundwork for a robust e-commerce application. As we wrap up this exploration of object-oriented programming principles in Java, it is essential to emphasize the significance of these concepts. They form the foundation for building scalable and maintainable software applications. By leveraging encapsulation, abstraction, inheritance, and polymorphism, developers can write code that is clean, understandable, and ready for growth. Remember, the essence of good software design is not just in what you create, but how you create it. Embracing object-oriented principles allows you to develop solutions that are not only efficient, but also elegant. So as you dive deeper into coding, keep these principles close to your heart. Practice and explore them in your projects, and over time you'll find that a solid grasp of these concepts will profoundly impact your software development journey. Happy coding! In today's lesson, we are going to explore the significance of design patterns in software development. Design patterns offer proven solutions to common problems that developers face, helping to create software that is not only robust but also easier to maintain. This is crucial because, as we've learned, software can rot over time without proper structure and best practices. So far, we learned about the core principles of object-oriented programming, which include encapsulation, abstraction, inheritance, and polymorphism, and their importance in creating structured, maintainable, and efficient code. We illustrated these concepts using Java examples, demonstrating how encapsulation protects data, abstraction simplifies interactions, inheritance promotes code reusability, and polymorphism enhances flexibility. Additionally, we discussed the application of these principles in building a clear and maintainable e-commerce platform structure. Understanding and applying these principles is crucial for effective software design and development. Now, we will talk about the significance of design patterns and how they can help avoid the software rot. Now let's take a look at how we can implement the Singleton pattern in Java. This design pattern ensures that a class has only one instance and provides a global access point to it. In this implementation, we have a class named Singleton that contains a private static variable instance which holds the single instance of this class. The constructor for Singleton is private, effectively preventing any other class from directly instantiating it. To enable access to the instance, we define a public static method called getInstance. This method first checks if the instance variable is null, meaning no instance has been created yet. If it is null, the method proceeds to create a new instance of Singleton. On subsequent calls to getInstance, since the instance already exists, it simply returns the existing one. This approach ensures that only one instance of Singleton can exist, making it perfect for managing shared resources like configurations or database connections. By using the Singleton pattern, we maintain control over resource usage and ensure consistency throughout the application. Now let's take a look at how we can implement the factory method design pattern to handle notifications in our application. We start by creating an abstract class called notification, which defines a method notifyUser that must be implemented by all concrete notification classes. This abstraction ensures that each notification type will have a consistent interface for sending notifications. Following the abstract class, we define two concrete implementations, email notification and SMS notification. Each of these classes provides its own implementation of the notifyUser method, encapsulating the specific behavior required to send an email or SMS notification. This approach illustrates the power of polymorphism, as we can treat different notification types uniformly through the abstract class. Next, we introduce the notification factory, a factory class responsible for creating instances of notifications based on a given type. The method createNotification takes a string parameter and returns the corresponding notification object. If the type is email, it instantiates email notification, and if it's SMS, it creates an instance of SMS notification. This design allows for easy extensibility. For instance, if we want to add a new notification type, we simply create another class extending notification and update the factory method, showcasing the maintainability provided by the factory method pattern. Now let's explore the implementation of the observer pattern through a practical example involving a temperature sensor and display units. In this code, we define an observer interface that mandates an update method, allowing different objects to respond to notifications when the monitored temperature changes. Next, we create the temperature sensor class, which holds a list of its observers in an array list. This class is responsible for adding and removing observers, as well as notifying them of changes via the setTemperature method. When the temperature is updated, the sensor calls the notifyObservers method, triggering each observer's update method, ensuring all attached display units reflect the latest temperature instantly. Now let's look at how the displayUnit class implements the observer interface. Each display unit has a name and outputs a message indicating its updated temperature whenever it receives a notification. This structure demonstrates how the observer pattern minimizes coupling between the sensor and display units, facilitating easy extensions or changes without affecting existing code. In summary, this implementation exemplifies a clean separation of concerns, aligning perfectly with the principles of object-oriented design. Now let's see how we can implement the strategy pattern in our sorting application. First, we define an interface named sorting_strategy that declares a method for sorting an integer array. This interface serves as a contract for all concrete sorting strategies, ensuring they all implement the same sorting functionality. Next, we have two classes, BubbleSort and QuickSort, both of which implement the sorting_strategy interface. Each class provides its specific logic for sorting an array, BubbleSort and QuickSort, respectively. This encapsulation allows us to separate the sorting algorithms from the sorter class, making it easier to maintain and extend. The sorter class holds a reference to a sorting strategy object. It includes a method to set the sorting strategy dynamically, enabling the user to choose which sorting algorithm to use at runtime. The sort method delegates the actual sorting task to the currently set strategy. This design allows for flexibility and adaptability, making it simple to add new sorting methods in the future without modifying existing code. This approach not only promotes clean code, but also enhances maintainability in our application. To understand the significance of these design patterns further, let's reflect on their impact on software development practices. By following design patterns, developers avoid common pitfalls and create applications that stand the test of time. Design patterns establish best practices that promote a shared language among developers, making code easier to understand and collaborate on. Imagine joining a new team where everyone used design patterns appropriately. You'd feel much more comfortable diving into their code because you'd immediately recognize the structure and the rationale behind their choices. This shared understanding enhances team efficiency, reduces onboarding time for new members, and ultimately leads to higher quality software. Now let's circle back to the concept of software rot. As we mentioned earlier, software can deteriorate due to a lack of structure or poor design. Design patterns act as a remedy for this issue. By providing established solutions for common problems, they guide developers in creating code that is not only functional but also straightforward and easy to modify. Using design patterns, coupled with the principles of object-oriented programming we discussed earlier, leads to a natural synergy that cultivates a cleaner architecture. We build systems that can gracefully evolve over time, allowing for new features, bug fixes, and optimizations without the looming threat of spaghetti code lurking in the shadows. So as you embark on your programming journey, remember that design patterns are your friend. They will serve as a compass guiding you through the intricate landscape of software development. Embrace them, practice applying them in your projects, and watch as your code becomes more elegant, maintainable, and scalable. You'll be the developer with the art of the code, crafting masterpieces that stand the test of time. The solid principles are essential guidelines for software development, aiming to create systems that are not only efficient, but also sustainable, reusable, and extensible. In this lesson, we will delve deep into the solid principles, exploring each component with clarity and practical examples to optimize your understanding. So far, we learned about the significance of design patterns in software development, emphasizing their role as reusable solutions to common problems. We explored the Singleton pattern for managing single-instance classes, the factory method pattern for creating objects while promoting loose coupling, and the observer and strategy patterns for event handling and algorithm selection, respectively. Additionally, we discussed how these design patterns establish best practices that enhance code maintainability and clarity. Overall, applying design patterns fosters a collaborative coding environment and helps prevent issues like software rot. Now we will cover the solid principles and how they guide developers in crafting high-quality software. Now let's see how we can implement the single responsibility principle (SRP) in our code. Initially, we had a user service class that combined two distinct responsibilities: user authentication and sending email notifications. This design creates challenges in maintenance and increases the risk of bugs when changes are made to either functionality. To adhere to SRP, we can refactor this code into two separate classes, the Authenticator class and the Email Service class. The Authenticator class will focus solely on user authentication, containing methods that handle the login process. This ensures that any changes to authentication logic do not affect other parts of the system. Meanwhile, the Email Service class will be exclusively responsible for sending emails, allowing us to modify email-related functionalities independently. By separating these concerns, we enhance code clarity and maintainability. Each class now has a single responsibility, enabling easier testing and modification. Therefore, following SRP not only leads to cleaner code, but also fosters a more organized structure that can adapt to future changes without unnecessary complications. Next, we will explore how to implement the open-closed principle in our shape drawing application. Initially, we have a shape drawer class that contains methods for drawing specific shapes, such as circles and rectangles. However, this design poses a limitation. To introduce new shapes, we would need to modify the existing shape drawer class, which could introduce potential bugs and violate the principle of being closed for modification. To address this, we will introduce a shape interface that defines a draw method, allowing us to create specific shape classes like circle and rectangle, each implementing this interface. Now, instead of the shape drawer relying on specific methods for each shape, it will utilize a single method that takes any object that implements the shape interface. This design enables the shape drawer to draw any shape without altering its structure when adding new shapes. By following this approach, if we want to include additional shapes like triangles, we will simply create a new class for the triangle that also implements the shape interface. This fosters a flexible and extensible system, showcasing the power of polymorphism while maintaining adherence to the open-closed principle. Now let's take a look at how the Liskov substitution principle can be illustrated through a rectangle and square example. Initially, we have a rectangle class with methods to set its width and height, as well as to calculate its area. This class offers a straightforward implementation of geometric shapes. However, we introduce a square class that extends rectangle, overriding the set width and set height methods to ensure that both dimensions remain equal, as is the case for squares. At first glance, this may seem appropriate, but it violates the Liskov substitution principle because substituting a square for a rectangle can lead to unexpected behavior in functions designed solely for rectangles. When we set the width or height of a square, both dimensions change simultaneously, which is not the case for rectangles. To adhere to this principle, we redesign our approach by creating a shape interface that both rectangle and square implement. This allows each class to maintain its own logic for calculating the area, while ensuring both can be used interchangeably in any context that requires a shape, promoting better structure and compliance with the Liskov substitution principle. Now let's take a look at a practical example of the interface segregation principle in action through our vehicle interface. Initially, we have a vehicle interface that encompasses both driving and sailing functionalities, which leads to confusion. For instance, our car class implements this interface, but when it encounters the sail method, it must throw an exception since a car cannot sail. Similarly, the boat class faces the same issue with the drive method. This demonstrates a clear violation of the interface segregation principle, as both classes are forced to implement methods that do not pertain to them. Next, we will refactor this structure by creating two separate interfaces, land vehicle and water vehicle. In this new design, car will implement only the land vehicle interface, allowing it to focus solely on the drive method. Concurrently, the boat will implement the water vehicle interface and provide its respective sailing functionality. This separation of concerns not only aligns with the interface segregation principle, but also enhances code readability and maintainability, ensuring that each vehicle class only deals with the methods relevant to its operation. Now let's explore how we can implement the dependency inversion principle in our code design. Initially, we have a notification service class that directly creates an instance of email service to send notifications. This approach couples the notification service to a specific implementation, making it difficult to adapt if we wish to change the method of notification, such as switching from email to SMS. To improve flexibility and adhere to the principle, we introduce an abstraction in the form of a notification interface. Both email service and SMS service then implement this interface, providing their specific notification logic. With this structure in place, the notification service class no longer relies on concrete implementations. Instead, it accepts any implementation of the notification interface through its constructor. This change allows us to easily switch between different notification methods without modifying the notification service class. As a result, our code becomes more decoupled and maintainable, fostering an architecture that can easily accommodate future changes in notification methods without impacting existing functionalities. This design showcases how applying the dependency inversion principle can significantly improve code quality. In conclusion, we've covered the core solid principles that lay the foundation for building sustainable, reusable, and extensible software applications. The single responsibility principle encourages clean code with distinct responsibilities. The open-closed principle allows us to extend functionality without modifying existing code, while the Liskov substitution principle ensures that subclasses can be used interchangeably without issues. The interface segregation principle promotes the creation of specialized interfaces, preventing bloated and unwieldy class structures. Finally, the dependency inversion principle fosters flexibility by emphasizing abstractions over concrete implementations. By understanding and applying these principles, you will create a robust architecture that can handle future changes with ease, enhancing both the maintainability and scalability of your software projects. So now, it's time to apply these principles in your own projects, creating exceptional software that stands the test of time. Happy coding. The Java platform is a powerful tool for developers, providing a robust ecosystem for building versatile applications. In this lesson, we'll dive into an overview of Java development, focusing on its core components and how they interconnect to create a seamless computing experience. So far, we learned about the importance of design patterns as reusable coding solutions for common software development challenges. We covered various design patterns, including the Singleton, factory method, adapter, observer, and strategy patterns, illustrating how each addresses specific issues while promoting code reusability and maintainability. Additionally, we emphasize the significance of adhering to the solid principles to foster cleaner and more scalable code. By implementing these patterns, developers can enhance the robustness and adaptability of their applications. Now we will talk about the fundamental aspects of the Java platform that make these design patterns and solutions possible. Now let's take a look at a simple Java program that prints a greeting message to the console. The code defines a public class named Hello World, which is the standard entry point for any Java application. This class contains the main method, marked as public static void main string args. The main method is crucial as it serves as the starting point for the program's execution. Within the main method, we utilize the system out println statement to send the string Hello World to the console. This method is part of Java's standard output stream, allowing developers to display messages and output information to users. The statement effectively shows how we can interact with users and provide output from our applications. By compiling this code using the javac command and running it with the java command, a user will witness the message displayed in the console, demonstrating the basic functionality of Java applications. This practice showcases the simplicity and efficiency of Java programming, laying the groundwork for more complex projects as we continue to explore the language's capabilities. Now let's see how we can allocate memory for our Java application by using the Java command line options. In the command java xmx 512m hello world, we are executing the compiled Java program hello world, while specifying a key parameter that directly influences its memory management. The xmx 512m option indicates that we are setting the maximum heap size available to the Java Virtual Machine, JVM, to 512 megabytes. Memory management is an essential aspect of Java development, and it plays a significant role in the overall performance of our applications. By allowing the JVM to manage memory allocation efficiently, we can help prevent issues such as memory leaks and ensure that our application runs smoothly. This command not only launches the Hello World application, but optimizes how it utilizes system resources based on our specified memory allocation. Understanding these command line options equips you with the ability to fine-tune your Java programs, allowing you to tailor their resource requirements based on the specific needs of each application and ensure an efficient execution environment. Now let's see how we can compile our Java program and create a Java file, which is essential for packaging and distributing Java applications. The first command, javac hello world java, compiles the Java source file named hello world java. This process converts the human-readable Java code into bytecode, resulting in a file named hello world class. This bytecode is the intermediary format that the Java Virtual Machine, JVM, understands, allowing our application to be platform independent. Next, we take this a step further by using the jar command, specifically jar cvf hello world jar hello world class. In this command, the C flag indicates that we want to create a new archive, V enables verbose output to check the progress, and F specifies the file name for the archive we're creating. The hello world class file is then included in the new jar file, hello world jar. This packaged jar file not only contains the compiled class but is also portable, meaning it can be executed on any system that has a compatible Java runtime environment, JRE. This encapsulation is vital for sharing your applications, ensuring that all necessary components are bundled together in a single file. Now let's take a look at a simple Java program that illustrates the core components of a Java application. The program defines a public class named example, which is a common starting point for Java applications. Within this class, we implement the main method, which serves as the entry point for any Java program. This is crucial because it's where the JVM begins execution when the application is run. Inside the main method, we use the system out println statement to display a message to the console, example class loaded. This line demonstrates a fundamental concept in Java, outputting data to the user interface, allowing developers to communicate the status of the program effectively. When this program is executed, the class loader first checks if the example class file is already loaded into memory. If it's not loaded, the class loader will load it, linking it to the Java virtual machine and resolving any dependencies before executing the main method. This process highlights the seamless interaction between the Java class file, the class loader subsystem, and the JVM, showcasing the efficiency and design of the Java architecture. Now let's see how we can implement a straightforward example to understand the concept of garbage collection in Java. In this example, we define a class called garbage collection example, which serves as a simple demonstration of how objects are created and subsequently made eligible for garbage collection. Within the main method, we first create an instance of garbage collection example and assign it to a variable named obj. At this point, the object is in use and the Java virtual machine JVM manages its memory. However, when we set the variable obj to null, we indicate that the reference to this object is no longer needed. This step is crucial because it makes the object eligible for garbage collection, meaning that the memory it occupies can be reclaimed by the JVM. To suggest that the garbage collector should run, we call system.gc. It's important to note that this is merely a request to the JVM. It does not guarantee that the garbage collector will execute immediately. This code showcases the automatic memory management process in Java, allowing developers to focus on the logic of their programs instead of manual memory handling. Understanding this concept is vital for writing efficient applications and ensuring optimal memory usage. Now we've covered the essential components of the Java platform and how they interact with each other. Each piece plays a crucial role in making Java one of the most popular programming languages for developers around the world. As we look forward, understanding these foundational elements equips you with the knowledge needed to develop efficient programs, leverage design patterns, and manage resources effectively. In summary, the Java platform consists of three main parts: the JVM, which executes Java bytecode, the JRE, which provides the necessary environment for running Java applications, and the JDK, which offers the tools needed for developing them. By mastering these components, you are well on your way to becoming proficient in Java development. In our next session, we will explore advanced features of the Java language, including multithreading and concurrency, that can further enhance your programming toolkit and application performance. Let's dive deeper into the fascinating world of Java. Now let's take a look at a practical example of Java memory management through our memory management example class. In this demonstration, we create an instance of myClass within the main method. When we execute new myClass, a new object is allocated in heap memory, exemplifying how Java dynamically manages memory allocation for objects. The obj variable residing on the stack holds a reference to this heap-allocated object. Next, when we call the display method on the obj instance, we witness the output confirming the creation of the object in heap memory. This highlights the importance of understanding how Java separates the stack and heap in memory management. The stack is responsible for method execution and local variables, whereas the heap allows for dynamic object allocation, which is crucial for functionalities requiring longer object lifecycles than a single method call. This simple yet insightful example reinforces our grasp of key memory management concepts, emphasizing the role of the JVM in handling memory efficiently and providing a foundational understanding necessary for writing robust Java applications. Understanding such principles will guide us in optimizing our code and managing memory more effectively in future lessons. Now let's take a look at an example demonstrating the garbage collection process in Java. In the garbage collection demo class, we define the main method, which serves as the program's entry point. Here we create an instance of garbage collection demo and invoke the createObjects method. This method's purpose is to generate multiple temporary string objects in a loop. As each string is created, it is stored in a local variable named temp. However, once the createObjects method completes, all these string references go out of scope and become eligible for garbage collection, meaning they are no longer accessible by the program. To illustrate garbage collection in action, we include a call to system GC, which suggests to the Java Virtual Machine JVM that it may want to run the garbage collector to free up memory. It's important to note that while this is a request to perform garbage collection, the JVM ultimately decides when to execute it. After suggesting garbage collection, we print a message confirming that the suggestion has been made. This simple demonstration showcases how Java manages memory automatically and highlights the impact of scoping on object lifetime and memory reuse. Now let's take a look at an example that illustrates how memory leaks can occur in Java. In this code, we define a class named MemoryLeakDemo, which contains a static list called LeakList, initialized as an array list. During the execution of the program, specifically in the main method, we call the method createLeakedObjects. This method is designed to add 1,000 string objects to LeakList, each labeled with object followed by its index. However, the key issue arises from the absence of a mechanism to clear LeakList after its use. As the method gets invoked repeatedly without any removal of items, the size of LeakList continues to grow indefinitely. This growth results in increasing memory consumption as more objects are retained in memory, preventing them from being garbage collected. Consequently, this could lead to performance degradation of the application over time. To demonstrate good practices, it is essential to remind ourselves always to clear lists when they are no longer needed, or consider using weak references where appropriate, thereby avoiding resource wastage and optimizing the overall performance of Java applications. Now let's implement a simple example to demonstrate data synchronization in a multi-threaded environment. We start by defining a counter class that contains a private integer variable count, initialized to 0. To ensure thread safety when incrementing this variable, the increment method is marked with the synchronized keyword. This means that only one thread can execute this method at a time, preventing any potential race conditions where multiple threads might try to update count simultaneously. Next, we create a synchronized demo class with a main method that sets up our multi-threading scenario. Here we instantiate our counter object and create two threads, T1 and T2. Each thread is tasked with calling the increment method 1,000 times. When both threads are started, they increment the shared count, but thanks to our synchronized method, we can be confident that no increments will overlap, thus maintaining data integrity. Finally, we wait for both threads to finish using the join method before printing out the final value of count. By the end of this program, we can expect the output to reliably show 2,000, reflecting the total number of increments made across both threads. This example beautifully illustrates the significance of synchronization in preventing inconsistent data states in a multi-threaded application. Now let's see how we can implement a thread-safe counter using the lock interface from Java's Java util concurrent locks package. We begin by defining a lock counter class that contains an integer variable count, initialized to 0, and a reentrant lock instance named lock. This lock will help us manage access to the counter in a multi-threaded environment. In the increment method, we employ the lock to acquire the lock before performing the increment operation on the count. Using a try-finally block ensures that the lock is always released, even if an exception occurs during the increment. This approach provides more control compared to the traditional synchronized keyword, allowing for advanced concurrency mechanisms, such as attempting to acquire the lock with timed waits. Moving on to the lock demo class, we create two threads that each increment the counter 1,000 times. After starting both threads, we join them to the main thread, ensuring that the main thread waits for them to finish. Finally, we print the final count, which, if our locking is effective, should total 2,000. This example illustrates how locks provide a robust mechanism for managing shared resources and ensuring data consistency in a concurrent application. Now let's see how we can implement a simple example using the volatile keyword to manage memory visibility between threads. In this code, we define a class VolatileDemo that contains a volatile Boolean variable named flag. This ensures that changes made to this variable by one thread are immediately visible to other threads. Within the VolatileDemo class, we have two methods, writer and reader. The writer method sets the flag to true, indicating that some condition has been met. Meanwhile, the reader method checks the value of flag. If flag is true, it prints a message to the console, confirming that the writer has updated the value. Next, we create a volatile example class with the main method. where we instantiate volatile demo and create two threads, write a thread and read a thread. We start both threads, allowing them to operate concurrently. By using the volatile keyword in our flag variable, we ensure that even though the threads run independently, the reader will always access the most recent value set by the writer, demonstrating the importance of proper memory synchronization in Java multithreading. Now let's summarize our understanding of Java memory management. We explored essential concepts such as how Java manages memory through the stack and heap, automated garbage collection, and the risks of memory leaks. We emphasized the importance of proper data synchronization in multi-threaded environments and how Java provides tools like the synchronized keyword, locks, and volatile variables to help manage concurrency and data visibility. The real genius behind Java's memory management system is its focus on reducing the burden on the developer while maximizing the efficiency and reliability of applications. With a solid understanding of these memory management principles, you can write Java applications that are not only efficient, but also scalable and maintainable. Remember, mastering these concepts will set you apart as a Java developer and prepare you for more advanced topics, such as performance tuning and multithreading. In our future lessons, we will explore these advanced features in depth, continuing our journey through the fascinating world of Java. In our exploration of Java, we have touched upon various crucial topics that form the foundation of efficient programming. So far, we learned about the Java platform's core components, including the JVM, JRE, and JDK, which are essential for understanding efficient Java development. We examined Java memory management, focusing on key concepts like the stack and heap, automated garbage collection, and the risks of memory leaks. Additionally, we covered the importance of data synchronization in multi-threaded applications, utilizing tools such as the synchronized keyword, locks, and volatile variables to maintain data consistency. Finally, mastering these principles will prepare us for more advanced topics in Java development. Now we will talk about the Java collection framework, an indispensable part of Java programming that helps us manage groups of objects efficiently. To begin with, it's essential to understand that collections in Java are a way to store and manipulate groups of objects. In Java, an array is represented by a sequence of the same type of positional index elements. They are a great way to store elements, but they have limitations in flexibility and ease of use. The Java collection framework, however, provides a richer set of functionalities that allows developers to work with data in a more flexible manner. With collections, we can handle dynamic data, allowing us to resize and access elements easily. Now let's see how we can implement the list interface using the ArrayList class in Java. In the provided code, we start by importing the necessary ArrayList class from the Java util package. We create a public class named ListExample, which contains the main method where the execution begins. Inside the main method, we instantiate an array list called fruits that will hold a list of strings. The code demonstrates how we can add elements to this list using the add method, including duplicates like apple. This points out the list's ability to maintain the insertion order and allow duplicates seamlessly. Afterward, we print the full list of fruits to the console, giving us a clear view of our collection. We then introduce the concept of accessing elements by their index. For example, we retrieve the first fruit in the list, demonstrating how we can navigate through our collection conveniently. Finally, we showcase the removal of an element with the remove method, illustrating how dynamic resizing allows us to modify our list easily. This practical example emphasizes the flexibility and efficiency of the list interface in handling groups of objects. Now let's take a look at how we can implement a hash set in Java to illustrate the concept of the set interface. In the given code, we first import the hashset class from the Java collections framework. The main method begins by creating a new hash set named colors, which is designed to store strings representing color names. As we proceed, we demonstrate how to add elements to the set using the add method. Importantly, notice that when we attempt to add red a second time, the hash set ignores this duplicate. This behavior exemplifies the core feature of a set. It ensures all elements are unique, which can prevent redundancy in data management. Next, we utilize the system.out.println method to display the contents of the colors set. The output will only show the unique colors because hashset does not allow duplicates. We also include a check for the presence of a specific color, blue in this case, using the contains method, which efficiently checks for the existence of an element within the set, showcasing the performance benefits of using hashset over lists. This code effectively demonstrates the basic operations of a hash set, reinforcing our understanding of the set interface within the Java collection framework. Now let's implement a basic queue using the linked-list class, which serves as a concrete implementation of the queue interface. In this example, we begin by creating an instance of a queue that will hold string elements. Through the offer method, we add 3 elements, first, second, and third, to our queue. This method adds the specified element to the end of the queue and is essential for managing data in a FIFO manner. After adding the elements, we display the current state of the queue to illustrate the order in which the elements are stored. Next, we utilize the poll method to remove and return the head of the queue, which is the first element added. This is a crucial operation, especially in scenarios like task scheduling, where processing order matters. We then print the removed element to show what has been taken from the queue, and finally, we display the updated state of the queue to confirm that the removal was successful and that the queue now retains its FIFO structure. This implementation highlights the efficiency and simplicity of using a linked list for queue operations in Java. Now let's implement a hash map to manage fruit stock levels. In this example, we create a hash map named stock that associates strings representing fruit names with integers indicating their respective quantities. First, we initialize the hash map, which utilizes an efficient data structure for rapid retrieval and insertion of entries. Next, we add items to our map using the put method, specifying the fruit names and their quantities. Each fruit name serves as a unique key, while the associated quantity is the value linked to that key. Following this, we display the entire stock map to give us a quick overview of the current fruit inventory. To access specific data, we demonstrate how to retrieve the quantity of apples using the get method. This allows us to query the hash map efficiently by providing the key. Finally, we can also manage our data by removing entries from the hash map with the remove method, which exemplifies how we can update our stock dynamically. This operational capability makes hash maps incredibly useful for managing relationships between two entities, such as fruit names and their corresponding quantities in this scenario. While working with collections in Java, performance can be a key consideration. Choosing the right collection depends on the specific use case, like whether you need to maintain order, allow duplicates, or require fast access based on key-value pairs. The behind-the-scenes implementation of these collections has a significant impact on how your application behaves, especially in terms of speed and efficiency. It is important to note the performance characteristics of various collections. For example, accessing elements in an array list is typically O1 because it uses an index, while searching through a linked list is ON due to its sequential nature. HashMap allows for constant-time complexity O1 for basic operations, but the performance can degrade if many elements hash to the same bucket. Now let's take a look at how we can use the Stream API to efficiently filter a list of names. In this example, we first create an array list named names, where we add several names including Alice, Bob, Charlie, and David. The key feature of the Stream API comes into play when we want to filter this list to retrieve only those names that start with the letter A. To accomplish this, we invoke the Stream method on our list, which converts the list into a stream of data that can be processed in a functional way. We then apply the filter method, providing a lambda expression that defines our condition. We want to include only names that meet the criteria of starting with A. This approach showcases the expressive power of streams, allowing us to write clean and concise code. Finally, we utilize the collect method with collect_list to gather the filtered results back into a new list called filtered names. The outcome is printed to the console, demonstrating how efficiently we can manipulate collections and filter data with modern Java programming techniques. This method not only simplifies the code, but also enhances performance when dealing with larger datasets. Now that we've explored the basics of the Java collection framework, it's essential to understand how to choose the right collections for your specific needs and how to utilize them effectively. Implementing the correct data structure can result in cleaner code, better performance, and simpler maintenance. As a developer, you shouldn't just stop at the basic collections, but should also explore additional data structures provided by the Java collections framework, like linked hash set, tree set, and array deck. These structures offer unique features tailored for specific scenarios. In conclusion, the Java collection framework is a vital tool that enhances our programming capabilities significantly. By providing a rich set of interfaces and classes for data handling, we can create more flexible, efficient, and maintainable applications. Whether you're dealing with lists, sets, queues, or maps, understanding how to leverage these collections is paramount to becoming a proficient Java developer. So now, with the knowledge of the Java collection framework, you're better equipped to handle the complexities of data in your applications. Don't forget to think about the structure of your data and the operations you need to perform when selecting the right collection type. Keep experimenting, keep coding, and enjoy the journey towards mastering Java programming. Now let's take a look at the bank account with lock class, which demonstrates how to safely manage concurrent access to a bank account's balance. Within this class, we define a reentrant lock, which is essential for ensuring that only one thread can execute the withdraw method at a time. This is important in multi-threaded environments, where multiple threads may attempt to withdraw funds simultaneously. Next, we implement the withdraw method, where we first acquire the lock by calling lock. This prevents other threads from entering this method until the current thread finishes its operation. Inside a try block, we check if there are sufficient funds to complete the withdrawal. If so, we deduct the specified amount from the balance. If the balance is insufficient, we display a corresponding message. Regardless of whether the operation succeeds or fails, the finally block ensures that the lock is released, allowing other threads to access the method, which is crucial for avoiding potential deadlocks. In the main method of the bankwithlock example class, we initiate two threads that both attempt to withdraw money from the same account. This illustrates the benefit of using reentrant lock in preventing race conditions, ensuring thread safety in the bank account operations. Now let's take a look at how we can utilize concurrent hash map for concurrent access in our applications. In this example, we start by creating an instance of concurrent hash map, defining it to hold key-value pairs where the key is a string and the value is an integer. We then define a runnable task that uses a loop to put 5 entries into the map. Each entry is uniquely identified by the thread name combined with a key index, ensuring that multiple threads can operate on the map concurrently without interference. Next, we instantiate two threads and assign them the previously defined task, allowing both threads to put entries into the map simultaneously. After starting both threads, we use join to wait for their completion, ensuring that all entries have been added before proceeding. Finally, we print the state of the map, showcasing how concurrent hash map efficiently manages multiple concurrent write operations. This implementation exemplifies the strengths of concurrent hash map, which allows safe access to the map without requiring manual synchronization, making it more performant and simpler to use for concurrent programming. Now let's take a look at how we can implement an executor service in Java to manage concurrent tasks efficiently. In our example, we begin by creating a fixed thread pool with 2 threads, which allows us to run multiple tasks without manually managing thread creation. We define a simple runnable task that prints the name of the thread executing it, demonstrating how tasks can be submitted for concurrent execution. Next, we submit this task to the executor 3 times. This will utilize the available threads in the pool to execute each task. The beauty of executor service lies in its ability to handle the complexities of thread management for us, allowing for a cleaner and more manageable code structure. After submitting the tasks, we call the shutdown method. This is crucial as it signals the executor to stop accepting new tasks while allowing the currently running tasks to complete gracefully, ensuring that resources are managed efficiently. This pattern showcases how using higher-level concurrency constructs like executors can lead to more robust and organized code, enhancing our ability to develop applications that leverage multithreading effectively. Next, we will implement a robust mechanism for handling exceptions in a multithreaded environment. In our example, we create a new thread that deliberately throws a runtime exception. To prevent the thread from terminating unexpectedly, we use a custom uncaught exception handler. By setting this handler, we can define what actions to take when an exception occurs in the thread. In this case, the handler logs the exception details, including the thread name and the error message. This approach enhances the robustness of our application by allowing it to manage errors gracefully rather than crashing. Instead of allowing the application to fail due to unhandled exceptions, we ensure that errors are captured and logged, which can be invaluable for debugging and maintaining stability in multi-threaded applications. This illustrates the importance of proactive error management within the concurrency model, as it fosters a more resilient application that can handle unexpected issues without abrupt interruptions. Now let's implement a simple example illustrating how to create a long-running task in a separate thread without blocking the main application thread. We begin by defining a class called longTask that implements the runnable interface, allowing us to encapsulate the task's behavior. Inside the run method, we use a try-catch block to simulate the task. The system out println statement indicates when the long task starts, followed by a thread sleep 5000, which pauses execution for 5 seconds, mimicking a time-consuming operation. This sleep duration allows us to see the impact of running this task in the background. Next, in the non-blocking task example class, we set up the entry point of our application. Here we create a new thread, passing an instance of long task to it. By calling start on this thread, we asynchronously initiate the long task, enabling it to run parallel to the main thread. Finally, we print a message to indicate that the main thread remains responsive and can continue processing other tasks while the long task executes. This design exemplifies the essence of concurrency, showcasing how background operations can be managed seamlessly in Java applications. In conclusion, Java concurrency is a powerful tool that allows developers to create responsive and high-performance applications. We've learned about the various ways to create and manage threads, the importance of synchronization, and how to manage shared resources gracefully. With constructs like executors, lock, and concurrent data structures provided by the Java util concurrent package, Java makes it accessible to build robust concurrent applications. Remember, mastering concurrency takes practice. It's essential to experiment, apply multi-threading concepts in real-world scenarios, and understand the implications of thread interactions in your applications. So dive into your next Java project, leverage these concurrency tools, and watch your applications come to life with improved performance and responsiveness. Happy coding! Let's dive into the exciting world of the Java Platform Module System, introduced with the release of Java SC9. This monumental upgrade, known as JSR 376 and part of the Jigsaw project, revolutionizes how we structure our Java applications. It partitions them into modules, formally defining how they interact while enhancing maintainability, security, and reliability. So far, we learned about Java concurrency, focusing on using reentrant lock for thread synchronization and the advantages of concurrent hashmap for concurrent data structures. We also explored executor service for simplified thread management and the importance of handling exceptions in multi-threaded applications through uncaught exception handler. Additionally, we emphasized the significance of non-blocking tasks to maintain application responsiveness, especially in user interfaces. Overall, these concepts are crucial for building robust and high-performance Java applications. Now let's implement a basic Java module using a module descriptor and an application class. First, we create a file named moduleInfoJava, which defines our module and its exported packages. In this case, we declare a module called moduleExample and specify that the example package is accessible to other modules. This is crucial as it sets the groundwork for encapsulation, clearly outlining which parts of our module can be utilized externally. Next, we create the application logic in a separate file named example-main.java. Here, we package our functionality in the example namespace. The main method serves as the entry point for our application, where it simply prints a welcoming message to the console. This setup not only demonstrates how to structure a module, but also emphasizes the isolation of code through packages. By defining our API with the exports directive, we ensure that any internal implementation can change without affecting other modules, reinforcing the encapsulation principle of modular programming. Let's delve into the process of compiling and executing our module. Initially, we will use the java command to compile our Java files. This command features the D flag, which specifies the output directory for the compiled classes. By selecting out as the designated directory, we can maintain an organized project structure, making it simpler to manage and locate our files in the future. Once the code has been compiled, the next step is to create a jar file for our module. We can accomplish this effectively using the jar command. Here we will specify the name of the jar file, which is moduleExample.jar, and employ the C flag to navigate to the output directory before packaging the classes. This process consolidates everything into a single file, facilitating easier distribution and execution of our module. To run our module, we can leverage the Java command. By indicating the module path using the module path flag and directing it to our jar, we can then specify the module and entry point we wish to execute. This organized approach illuminates how the different components of our module work in unison, showcasing the cohesive integration of compilation, packaging, and execution within the Java Platform Module System. Now let's take a look at how to define our module and its dependencies using a module descriptor. We start by creating a file named moduleInfoJava, which is essential for configuring the module in the Java Platform Module System, JPMS. Within this file, we declare our module with a unique name, in this case, moduleExample. Next, we utilize the exports directive to specify that the example package is publicly accessible. This means that other modules can see and use the classes and interfaces within the example package, promoting interaction between different parts of an application. Importantly, we also include the requires Java logging line. This directive informs both developers and the Java Virtual Machine JVM that our module depends on the Java logging module for its functionality. Such explicit dependencies enhance code clarity and prevent issues like version conflicts or class name clashes, ensuring that our module operates smoothly without running into class path hell. This approach not only fosters better modular design, but also significantly improves maintainability and security in our Java applications. Now let's take a look at how to define a module with clear visibility for its components. In this example, we specify a module named ModuleExample using the moduleinfo.java file. The exports directive indicates that the example API package is accessible to other modules, allowing external code to interact with its public classes. This is essential for creating a library as it provides a controlled interface for users. However, we intentionally do not export the example internal package, meaning that any classes within this package are hidden from external access. This encapsulation helps maintain the integrity of the module by preventing external dependencies on internal classes that might change, thereby ensuring stability and reliability. By structuring your module this way, you can craft a clean API while safeguarding your internal implementation details, making it easier to manage long-term changes without affecting users of your library. This design illustrates the strength of JPMS in fostering both clarity and security in module development. Now let's implement a simple logging module to better understand how modularization in JPMS promotes clean and maintainable architecture. First, we define our module with a descriptor that specifies the module's name as module logging and indicates that it exports the logging package. This export statement is crucial as it allows other modules to access the functionalities provided by our logging package while keeping the internal logic encapsulated and hidden. Next, we move to the implementation of our logger class within the logging package. Here, we create a public class called logger, which contains a method named log. This method takes a string message as a parameter and prints it to the console prefixed with log. This design adheres to the single responsibility principle by focusing solely on logging functionality, thereby simplifying maintenance and future enhancements. By integrating this logging module with other components of our application, we can introduce standardized logging capabilities without affecting the rest of the system. This modular approach encourages developers to keep components decoupled, enhancing overall application quality and architecture. Of course, while JPMS has immense benefits, it's not mandatory. If your existing application isn't ready to adopt JPMS yet, you can still manage it using unnamed modules, which allow you to continue leveraging the class path without restructuring your code into modules. In unnamed modules, all classes will belong to an unnamed module reading each readable module or class from the class path. This way, existing applications can maintain compatibility while gradually transitioning to the modular system. However, bear in mind that this is a temporary measure. The longer your application stays on the class path, the more difficult it may become to adopt the benefits of modularization later on. As we delve deeper into the JPMS, it's vital to recognize that it establishes a more secure code ecosystem. Because each module defines its accessibility rules, vulnerabilities caused by external access to internal functions can be mitigated. Additionally, it constructs an acyclic module graph, preventing cyclic dependencies that can complicate application structure and maintenance. When managing larger applications, knowing the dependency paths becomes crucial, and eliminating cycles makes things much more manageable. In conclusion, the Java Platform Module System introduces a transformative way to develop Java applications, fostering better organization, stronger encapsulation, and enhanced maintainability. It streamlines the dependency structure between components, advocating for clean architecture principles that lead to more robust applications. Particularly in complex systems, where various parts need to communicate without overexposing functionality, JPMS shines as a framework that addresses many of the long-standing issues encountered in the traditional Java development workflow. So as you embark on your journey with the JPMS, embrace its potential and enjoy crafting applications that are as maintainable and secure as they are powerful. Happy coding! In this video, we will dive into the fascinating world of creational design patterns in software development, particularly in Java. Creational design patterns are essential as they deal with object creation mechanisms, which can enhance flexibility and reuse. Understanding these patterns is key to building efficient and scalable applications. So far, we learned about the Java Platform Module System, JPMS, which was introduced in Java SC9 to improve application structure through modularization. We explored how modules encapsulate functionality, enhance maintainability, and prevent class path issues by enforcing explicit package-level dependencies. Additionally, we discuss the importance of strong encapsulation and how JPMS encourages best practices in application development while allowing for gradual adoption of modularization. Overall, JPMS represents a significant advancement in creating robust and scalable Java applications. Now we will talk about creational design patterns, which will give us insightful strategies for object creation. Let's begin with understanding why creational design patterns are important. Imagine you're building a complex application where many similar object instances are required. If you're not careful, you could end up with an inflexible codebase that's hard to maintain. Creational design patterns help by centralizing and controlling object creation, allowing you to create objects in a way that is scalable and efficient. The most commonly used creational design patterns include Singleton, Factory Method, Abstract Factory, Builder, and Prototype. Now let's implement the Singleton pattern in our configuration management. In the Configuration Manager class, we begin by defining a private static variable named instance, which will hold the single instance of the class. This is essential to ensure that only one instance of the Configuration Manager exists during the application's lifecycle. The constructor of the Configuration Manager class is made private, which prevents external classes from creating instances directly and guarantees that the Singleton property is maintained. To access the unique instance of the class, we provide a static method named getInstance. This method checks if the instance variable is null, indicating that no instance has yet been created. If that's the case, it initializes a new Configuration Manager object and assigns it to instance. Consequently, every time you call the getInstance method, you will either retrieve the existing instance or create it if it hasn't been initialized. This mechanism effectively controls object creation, ensuring that there's only one Configuration Manager managing the application's settings. Lastly, the displayConfig method can be used to demonstrate the functionality of the Configuration Manager, confirming that it's ready to display the application's configuration when needed. Now let's see how we can implement the factory method pattern to create different types of vehicles. In our code, we start with an abstract class called vehicle, which defines a common interface for all vehicles by declaring a method drive. This abstraction ensures that specific implementations will provide their unique behavior for driving. Next, we have two subclasses, car and truck. Each of these subclasses provides its own implementation of the drive method, which allows each vehicle type to exhibit distinct behavior when driven. For instance, when a car drives, it outputs driving a car, while the truck outputs driving a truck. To facilitate the creation of these vehicles, we introduce an abstract factory class, vehicle factory, which declares the method createVehicle. This method serves as a blueprint for subclasses tasked with concrete vehicle creation. In our implementation, we have two concrete factories, car factory and truck factory, which extend vehicle factory. Each of these factories implements the createVehicle method to instantiate either a car or a truck, respectively. This approach allows the client code to create vehicles without needing to understand the complexities of their instantiation, thus promoting loose coupling and easy extensibility. Now let's see how we can implement the abstract factory pattern, which is crucial for creating families of related objects without specifying their concrete classes. In our code, we start by defining a button interface, which establishes a contract for all button types. We then provide two implementations of this interface, Windows button and Mac OS button, each defining its own paint method that outputs the respective button's name to the console. Next, we define an abstract factory interface called GUI Factory, which includes a method createButton, meant to create buttons without dictating the specific class being instantiated. This abstraction allows for flexibility in the UI design. We then implement concrete factories, Windows Factory and Mac OS Factory, both of which implement the GUI Factory interface. Each factory provides its unique implementation of the createButton method, ensuring that the correct type of button is instantiated. This approach promotes code reusability and maintainability. By encapsulating the instantiation logic within the factories, you can easily switch between different UI themes without altering the core application logic. This encapsulation makes the code more scalable, as you can introduce new button types or factories with minimal disruption. Now let's see how we can implement the builder pattern in our application to manage the creation of complex objects like a user. In this implementation, we define a user class that encapsulates the properties of a user, such as username, email, and phone. However, we don't expose the constructor of the user class directly to enforce controlled creation. To facilitate this, we introduce a nested static class called userBuilder. This builder class requires the mandatory username when instantiated, ensuring that every user object has a unique identifier right from the start. Next, the userBuilder offers optional methods for setting other attributes, such as email and phone. These methods return the builder itself, allowing for method chaining, which results in more fluent and readable code. Finally, the build method in the userBuilder class constructs a new user instance using the properties set in the builder. This separation of construction and representation allows for a flexible object creation process, catering to various user scenarios with optional parameters, thus making our code cleaner and easier to manage. Now let's implement the prototype pattern, which allows objects to be cloned, facilitating the creation of new instances without the need for costly operations. We begin by defining a prototype interface that declares a clone method, which is essential for any class that intends to implement this pattern. This method allows the class to return a copy of itself. Next, we create a concrete class called Concrete Prototype, which implements the prototype interface. Within this class, we have a private field, sample field, that holds a string value. The constructor of Concrete Prototype initializes this field, allowing each instance to hold unique data. The crux of the prototype pattern lies in the clone method, where we create a new instance of Concrete Prototype using the existing object's sample field value. This method ensures that clients can create new instances of Concrete Prototype without needing direct access to its constructor, thereby maintaining flexibility and decoupling client code from specific classes. This pattern is particularly beneficial when object creation involves complex processes, allowing for efficient and streamlined cloning instead. In conclusion, creational design patterns offer invaluable strategies to manage the complexity of object creation in software development. By using patterns like Singleton, Factory Method, Abstract Factory Builder, and Prototype, developers can create flexible, maintainable, and scalable applications in Java. As we evolve in our understanding of these patterns, they will undoubtedly aid us in building more efficient and organized code. Thank you for joining me today. Don't forget to like, subscribe, and hit that notification bell for more tutorials. Next, we will venture into structural design patterns, where we'll learn how to compose classes and objects to form larger structures while ensuring flexibility and efficiency. The factory method pattern is an essential concept in object-oriented programming that helps manage object creation in a centralized manner, promoting greater flexibility and scalability in software design. In this lesson, we will explore this pattern, delving into its purpose, benefits, and practical implementation in Java programming. So far, we've covered the significance of creational design patterns in software development, focusing on various strategies for object creation that enhance flexibility and efficiency. We discussed the Singleton, Abstract Factory, Builder, and Prototype patterns, learning how they each provide unique approaches to handle object construction. Now we will dig deeper into the factory method pattern, demonstrating how it centralizes the instantiation of specific types, allowing for cleaner code and improved maintainability. Now let's see how we can implement the core elements of the factory method pattern with the delivery interface. This interface serves as the blueprint for all delivery types, ensuring that each concrete class will implement the deliver method. This approach allows us to treat different delivery methods uniformly in our application. Next, we will write the two concrete classes, truck delivery and ship delivery. Each class implements the delivery interface, providing its own specific behavior for the deliver method. When we call the deliver method on an instance of either class, it will execute the relevant code for delivering the package, which demonstrates the flexibility of our design. Now let's implement the abstract class delivery factory, which includes the factory method create delivery. This method is essential as it will be overridden by subclasses to return specific types of deliveries. We then create two factory classes, Truck Delivery Factory and Ship Delivery Factory, inheriting from Delivery Factory. Each factory creates and returns instances of their respective delivery types, adhering to the factory method pattern's principle of creating objects without exposing the instantiation logic to the client code. This encapsulation leads to cleaner, more maintainable code. Now let's see how we can implement the main class that utilizes our factory classes to create and manage different types of deliveries. In this code, we first create an instance of Truck Delivery Factory, which is responsible for producing truck delivery objects. By calling the create delivery method on this factory, we instantiate a truck delivery object and invoke its deliver method. This method prints a message indicating that the delivery is being made by truck. Next, we repeat a similar process with a ship delivery factory. This factory is tasked with creating ship delivery objects. We again call the create delivery method, which provides a ship delivery instance, and by calling its deliver method, we see a message indicating that the delivery is being made by ship. By relying on these factory classes, we've achieved a cleaner and more maintainable code structure that adheres to the factory method pattern. This approach highlights the separation of concerns, making it easier to expand our delivery options without directly altering the client code that utilizes these delivery objects. As a result, our application becomes more flexible and scalable. Now let's implement the drone delivery class, another delivery method that adheres to the same interface as our previous delivery types. This class implements the delivery interface and provides a specific behavior for the deliver method, which outputs delivering by drone when invoked. By creating this new class, we illustrate the open-closed principle, allowing us to introduce new functionalities without modifying existing code. Next, we'll create the drone delivery factory class, which extends the delivery factory. This factory will be responsible for producing instances of drone delivery. In this factory, we override the create delivery method to return a new instance of drone delivery, ensuring that our new delivery type is seamlessly integrated into the factory-based approach. Now let's see how we can utilize this new factory in our main application code. We introduce a new instance of drone delivery factory in the main class, similar to how we use the truck and ship factories. Calling the create delivery method on this factory allows us to create a drone delivery instance. When we call the deliver method on this instance, it displays the corresponding output, showcasing all three delivery methods in action. By doing this, we've successfully expanded our application while keeping the core code stable. One might wonder why we wouldn't simply instantiate classes directly instead of using factories. The answer often lies in the flexibility and maintainability that the factory method pattern provides. By centralizing object creation, we can easily manage changes in our classes, handle complex initialization, and enforce logical groupings of related objects. Furthermore, should you decide to switch to a different delivery mechanism or change delivery logic, the impact on the existing code remains minimal. You can just modify or add new factory methods without altering the core business logic, which is where code stability and scalability come from in larger applications. Let's touch briefly on potential scenarios where the factory method pattern shines brightest. Consider a user interface toolkit where you need a variety of components such as buttons, checkboxes, or text fields. By defining a common interface for these components and creating factory classes for different UI themes, e.g. Windows, Mac, and Linux, you can effortlessly swap themes or modify individual components without diving deep into the application logic. Furthermore, the pattern proves invaluable in managing resource initialization, especially when working with databases or creating objects that require heavy resources. Instead of creating them outside their respective classes every time, the factory can manage creation, initialization, and potentially resource pooling. While the factory method pattern is a valuable addition to your programming toolkit, it's essential to recognize potential drawbacks. Introducing abstract factories may increase the complexity of your codebase. For simpler situations where object instantiation is straightforward, the overhead may not always be justified. Therefore, it's critical to analyze the specific requirements and scale of your application to determine whether the factory method pattern is the right fit. In conclusion, the factory method pattern is a powerful design pattern that encapsulates the object creation process, enabling you to build scalable, maintainable applications. By centralizing how objects are instantiated, you not only simplify your code but also open the door for easier extensions and modifications. As you continue your journey in software development, keep this pattern in your toolbox for situations that demand robust object management and flexibility. Thank you for joining me in this exploration of the factory method pattern. Stay tuned for our next lesson, where we will dive into the fascinating world of structural design patterns, enhancing our ability to compose and manage objects and classes even more effectively. The builder pattern is a design pattern that simplifies the construction of complex objects. It allows for creating instances of a class step by step, rather than through a monolithic constructor that can become cluttered and hard to manage. In this session, we will unravel the intricacies of the builder pattern and demonstrate how it can effectively manage object creation, leading to cleaner and more maintainable code. So far, we learned about the factory method pattern, which centralizes object creation to enhance maintainability and flexibility in software design. We discussed how this pattern allows subclasses to alter the type of objects created without directly instantiating classes, using an interface and abstract classes. A real-world example demonstrated its practical implementation with delivery types, showcasing the ease of extension by adding new delivery modes. Finally, we touched on the advantages and potential drawbacks of using the factory method pattern in programming. Now we will dive into the builder pattern. Now let's take a look at how the house class is structured using the builder pattern. The class has three main properties: rooms, roof type, and color, which are declared as final to enforce immutability once the object is created. The private constructor accepts a house builder instance, allowing the builder to set these properties during construction without exposing the details in the main house class. Next, we define the house builder class as a static inner class to encapsulate the building logic. Inside this builder, we declare private variables corresponding to the attributes of the house. The builder provides fluent setter methods, each returning the builder instance itself to enable method chaining. This allows us to set multiple attributes in a clean, readable manner. The build method in House Builder is responsible for creating a new house object using the current state of the builder. It ensures that the builder's properties are properly assigned to the new house. Finally, the toString method in the house class is overridden to provide a string representation of the object, enhancing readability when we print the house instance. This structure exemplifies how to effectively separate construction logic from the object itself, promoting code clarity and maintainability. In this section, we will explore how to create a house object using the house builder. Within the main class, we define the main method, which acts as the starting point for our application. We create a new instance of house by utilizing the house builder. The builder is initialized with new house builder, and we proceed to customize the house's attributes using a series of setter methods: set rooms for, set roof type gable, and set color blue. This approach allows for method chaining, enabling a fluent expression of our intentions, and resulting in code that is both cleaner and more understandable. After configuring all the desired properties, we invoke the build method to obtain the completed house object. To showcase the created house instance, we use system.out.println house, which calls the overridden toString method from the house class. This outputs a well-formatted string representation of the house's attributes. This example not only highlights the advantages of using the builder pattern, but also underscores the enhanced clarity it provides in object construction compared to traditional bulky constructors. Now let's implement the validation logic within the build method of our house builder. This step ensures that the house cannot be created without specifying a valid number of rooms. Specifically, we introduce a check that throws an illegal argument exception if the number of rooms is less than or equal to 0. This validation enhances the robustness of our object construction process by preventing the creation of invalid house objects. With this safeguard in place, any attempt to build a house without an appropriate number of rooms will trigger an informative error message. This way, developers are immediately alerted to incorrect usage, thus maintaining the integrity of the house object and ensuring it always adheres to its defined rules. This validation feature aligns perfectly with the principles of the builder pattern, emphasizing that we can enforce business rules directly within the construction process, reinforcing the quality and reliability of the objects we are creating. By incorporating these checks, we contribute to better software design and reduce the potential for bugs down the line. Now let's enhance our house builder class to include additional optional features like a garage and a patio. This extends the flexibility of our builder, allowing users to customize their house without complicating the constructor. The house builder now includes two new Boolean attributes, has garage and has patio. Each of these new features has its own setter method, namely set has garage and set has patio, which accept Boolean values and return the builder instance, enabling method chaining. Next, we'll implement these changes into the main house construction process. When creating a new house, users can specify whether to include these optional features by calling the corresponding methods. For example, in our main method, we can create a house with 3 rooms, a hip roof, a green color, a garage, and no patio, all through a clear and fluent interface. This manner of constructing objects streamlines the creation process, making the code clean and maintaining readability. By organizing the configuration options in this way, developers avoid messy constructors, ensuring that each house can be tailored according to specific needs while remaining easy to understand and manage. Now let's take a look at how we can extend the functionality of our house builder by creating a specialized builder for luxury houses. In this code, we define the luxury house builder class, which inherits from the base house builder. This approach allows us to add unique features specific to luxury houses without altering the core implementation of the original builder. Within the luxury house builder, we introduce a private Boolean variable to indicate whether the house will have a swimming pool. To set this feature, we create the method setHasSwimmingPool, which allows callers to specify this attribute fluently, returning the luxury house builder instance for method chaining. This maintains the builder's fluid interface, making it easy to create a luxury house step by step. Furthermore, we override the build method to incorporate any additional validation required for luxury features. By doing this, we ensure that any specific requirements for building a luxury house are met before returning a new instance of house. This implementation exemplifies the open-closed principle by enabling extensibility while keeping existing builders untouched, thereby keeping our code both robust and maintainable. Now let's take a look at the private constructor for the house builder. This constructor is defined as private to restrict the instantiation of the house builder class outside the house class. By doing this, we enhance encapsulation, ensuring that clients cannot mistakenly create a house builder instance without following the appropriate construction process. This design choice promotes correct usage of the builder pattern, as clients will be required to use the static inner class method to create builders tied directly to the house. This pattern not only improves the integrity of object construction, but also aligns with best practices by limiting access to the builder only during the necessary construction phase. With the builder hidden and inaccessible from outside the house class, it reinforces the idea that the builder should solely be utilized to set up and configure the house object. This approach ensures that the created object remains immutable and prevents any unintended modifications after its instantiation, leading to a more robust and maintainable codebase. Now let's recap what we have learned about the builder pattern. It provides an efficient way of constructing complex objects step by step, helping to maintain clarity and separation of concerns. It allows for validation during the building process and can easily accommodate optional parameters and variations through subclassing. With a good understanding of the builder pattern, you can build clean and robust Java applications that are easier to maintain in the long run. So next time you're faced with the need to create complex objects, remember that the builder pattern is a powerful ally in your design toolkit. In our upcoming sessions, we will continue our exploration of design patterns, uncovering more strategies to refine your programming skills. Thank you for joining me today in our journey through the builder pattern. Now let's take a look at a basic implementation of the Singleton pattern in Java. In this example, we have a class named Singleton that contains a private static variable instance to hold the single instance of the class. The constructor of the class is defined as private, which prevents any external class from instantiating it directly. This is a crucial aspect of the Singleton pattern, as it ensures that only one instance of the object can exist. Next, we will implement a static method called getInstance, which serves as the global access point for obtaining the Singleton instance. When this method is called, it first checks whether the instance variable is null. If it is, this indicates that no instance has been created yet, prompting the method to create a new instance of the Singleton class. Conversely, if the instance already exists, it simply returns the existing instance. This design guarantees that no matter how many times getInstance is invoked, it will always provide the same instance, thus enforcing the Singleton behavior effectively. Now let's see how we can implement a thread-safe Singleton pattern in Java. The thread-safe Singleton class begins with a private static variable, instance, which will hold the single instance of the class. By making the constructor private, we prevent external classes from creating new instances. To ensure that our Singleton can be safely accessed from multiple threads, we introduce a synchronized method, getInstance. This method first checks if instance is null, and if it is, it enters a block where it initializes the instance. The use of the synchronized keyword guarantees that only one thread can execute this block of code at a time, thus preventing simultaneous access and potential multiple instantiations of the Singleton. While this approach effectively provides thread safety, it's worth noting that synchronization may introduce performance overhead, as threads may contend for access to the method. This implementation is ideal in scenarios where a single instance is critical, such as managing resource connections in an application, ensuring consistent access to a shared resource while maintaining integrity and performance in a multi-threaded context. Now let's take a look at how we can implement the double-checked locking pattern in our Singleton class to enhance performance while ensuring thread safety. In this implementation, we define a private static variable called instance, which is marked as volatile. This keyword is crucial. It prevents the Java virtual machine from performing optimizations that might lead to a partially constructed object being visible to other threads. The constructor is kept private to restrict instantiation from outside the class, maintaining the Singleton's integrity. The core of the pattern lies in the getInstance method. Initially, we check if instance is null, which indicates that the Singleton has not been created yet. If it is indeed null, we enter a synchronized block to ensure that only one thread can execute this section at a time. Inside this synchronized block, we perform another check for instance being null. This second verification is essential to avoid unnecessary synchronization overhead once the instance is created. If instance is still null, we proceed to instantiate the double-check locking Singleton. This approach facilitates efficient use of resources by limiting synchronization to the critical section, thus improving performance while preserving the thread safety that the Singleton pattern demands. Now let's implement a basic logger class utilizing the Singleton pattern. This logger will ensure that there is only one instance of the logging mechanism throughout the application, centralizing logging functionality and improving efficiency. In this implementation, we start with a private static variable named instance, which holds the single instance of the logger. The constructor is private, meaning no other class can create a new instance of logger directly. This encapsulation is key in enforcing the Singleton pattern. Next, we define a public static method called getInstance. Within this method, we first check if the instance variable is null. If it is, we create a new logger instance. This ensures that the logger is instantiated only once. The method then returns the existing or newly created instance, allowing other classes to access the logger easily. Additionally, we provide a log method that takes a string message as an argument and prints it to the console, prefixed by log. This method can be invoked from anywhere in the application using logger getInstance, log your message here. By centralizing this logging behavior, the logger class helps maintain a clean and consistent logging strategy across the application. Now let's take a look at how we can effectively utilize dependency injection to manage our logger instance in the application service class. This approach enhances testability and promotes better design practices by allowing us to decouple the dependencies of our class. In this implementation, we define a private final variable named logger, which will hold the reference to our logger instance. The application service class constructor takes a logger instance as a parameter and assigns it to our logger member variable. By doing this, we're not directly calling the Singleton's getInstance method within the service, which helps to avoid the tightly coupled architecture often associated with Singleton usage. When we invoke the doSomething method, the logger instance now passed through the constructor is utilized to log an important message, thus ensuring that our application's logging functionality is centralized and maintained through a single instance. This design not only facilitates unit testing, where we can easily inject a mock logger for testing purposes, but also results in cleaner, more maintainable code. As a result, employing dependency injection promotes a robust structure in our applications by enhancing reusability and simplifying future modifications. In a nutshell, the Singleton pattern is a valuable tool in software design, ensuring a class has only one instance and providing a global access point to it. We covered various implementations, including the basic, thread-safe, and optimized double-check locking approaches. Moreover, we demonstrated practical usage by implementing a logger and highlighted potential pitfalls like testing difficulties associated with Singleton usage. As you integrate this design pattern into your programming practices, always remember the balance between simplicity and the principles of good software design. Use it wisely where appropriate and remain vigilant for situations where other design patterns might be more fitting. The Singleton pattern can enhance your code's clarity and design, particularly in scenarios that demand a single shared instance. However, like any tool in your programming toolkit, understanding when and how to use it is crucial to writing clean, maintainable, and flexible code. Thank you for joining me today as we delved into the Singleton pattern. As we continue our exploration of design patterns, you'll find many more techniques and tools that will sharpen your programming skills and enhance your design approach. Stay tuned for what's next. Every piece of software has a purpose, or in other words, an expected behavior that it should fulfill. Design patterns serve as proven solutions to common problems in software design, enabling engineers to implement functionalities effectively and systematically. Each design pattern addresses a specific problem, offering a standard approach that can be reused across various programming contexts. Today's discussion is focused on getting an overview of design patterns, particularly emphasizing structural patterns, and how they can enhance code clarity and maintainability. So far, we learned about the Singleton pattern, which ensures that a class has only one instance and provides global access to it. We examined its implementation in Java, including basic and thread-safe variants, and discussed the importance of managing a single instance effectively to avoid resource wastage. Additionally, we highlighted practical usages such as managing logging functionalities while addressing potential drawbacks, particularly in testing environments. Moving forward, we'll explore more design patterns and their applications in software development, starting with structural patterns, which focus on composing classes and objects to form larger structures. Now let's take a look at how the adapter pattern can be implemented in Java to facilitate interaction between disparate classes. We start by defining an interface called engine with a method start. This sets a common contract that different types of engines must adhere to. Next, we create a petrol engine class that implements the engine interface, providing its own version of the start. method, which prints a message indicating the petrol engine is starting. However, we also want to integrate an electric engine class, which does not initially conform to the engine interface as it has a charge method instead. To resolve this incompatibility, we introduce the electric engine adapter, which implements the engine interface. This adapter contains an instance of electric engine and transforms its behavior into a format recognizable by the engine interface. When the start method of the adapter is called, it first invokes the charge method of the electric engine, followed by a message indicating that the electric engine is starting. In the vehicle class, we create a constructor that accepts an engine object, allowing us to instantiate vehicle objects with either a petrol engine or an electric engine wrapped in the adapter. When we demonstrate the functionality in the main method, we can see how both engine types operate interchangeably within the vehicle class, showcasing the flexibility provided by the adapter pattern. Now let's see how we can implement the bridge pattern to achieve flexibility in our code structure. We start by defining a vehicle interface that sets the contract for various vehicle types with a single method drive. Next, we create an abstract terrain class which contains a reference to a vehicle. This allows us to encapsulate the relationship between vehicles and terrains without tightly coupling them. We then implement two concrete vehicle classes, car and bike, each providing their own implementation of the drive method. With these vehicles established, we proceed to create specific terrain classes off-road and highway. Each of these subclasses extends the terrain class, utilizing the provided vehicle reference to invoke its drive method. This structure grants us the ability to represent vehicles on various terrains without modifying existing code. In the main class, we instantiate both a car and a bike, pairing them with respective terrain types. By invoking the drive-on-terrain method on these terrain instances, we see how vehicles can seamlessly interact with different terrains, showcasing the decoupled nature of the bridge pattern. This design enables future integration of new vehicle or terrain types without altering the core framework. Now let's implement the composite pattern, a structure designed to address part-whole hierarchies by treating individual objects and compositions uniformly. The code starts with an interface named component, which declares a method called display. This lays the groundwork for both individual parts and composite groups to share a common interface, enabling polymorphic behavior. Next, we define the leaf class, implementing the component interface. In this class, we have a private member variable name, which stores the identity of the leaf. The display method here simply prints out the name of the leaf. This class represents the basic element of our hierarchy. Following this, we introduce the composite class, which also implements the component interface. This class maintains a list of children other components, which can either be leaves or more composites, allowing nesting. The add method enables adding components to this list, while the display method iteratively calls display on each child, effectively showing a structured representation of the entire tree. In the main class, we demonstrate this pattern by creating a composite structure where we add two leaf components and then call display on the composite, showcasing how the composite pattern facilitates managing complex hierarchies in a clean and efficient manner. Next, we will explore the decorator pattern, which allows us to dynamically augment an object's behavior without modifying its underlying structure. This pattern is particularly useful for enhancing functionalities of objects at runtime, making it a flexible solution for scenarios like adding customizable features to products. Now let's implement the core elements of this pattern. We start with a coffee interface that defines two essential methods: getDescription, which returns a string describing the coffee, and cost, which returns the price. The simple coffee class is a concrete implementation of this interface, providing a basic description and cost for a simple coffee. We then create an abstract class called coffee decorator, which also implements the coffee interface. This class serves as a base for creating various decorators that enhance the core coffee object. The milk decorator and sugar decorator classes extend coffee decorator, overriding the methods to add milk or sugar to the coffee, thus modifying its description and cost accordingly. Finally, we demonstrate how to use these decorators in the main method. Initially, a simple coffee is instantiated and described. Then we apply the milk decorator and sugar decorator, showing how we can seamlessly enrich our coffee object with additional features while preserving the original object's functionality. This showcases the power and flexibility of the decorator pattern in action. Now let's take a look at how the facade pattern can simplify interactions with complex systems. We begin by defining two essential components, the amplifier and DVD player classes. Each of these classes has on and off methods to control their states, giving us a clear interface for interacting with these devices. Next, we implement the home theater facade, which serves as the intermediary between the client and the underlying subsystems. By holding references to the amplifier and DVD player, the facade provides high-level methods like Watch Movie and In Movie. When the client wishes to watch a movie, calling Watch Movie will activate both the amplifier and the DVD player without requiring the client to understand how to control each device directly. This encapsulates complexity, making the interaction seamless and user-friendly. Finally, in the main class, we instantiate the components in the facade. By calling the facade's methods, the user can easily turn on the home theater system to enjoy media, and just as easily turn it off when finished. This approach highlights the effectiveness of the facade pattern in simplifying interactions with multiple subsystems. The adapter pattern is an essential structural design pattern that facilitates communication between incompatible interfaces, allowing them to work together seamlessly. Imagine you have two devices that need to communicate but speak different languages. The adapter pattern acts as a translator, bridging the gap and enabling interaction. So far, we learned about various structural design patterns, including the adapter pattern, which enables incompatible interfaces to interact, and the bridge pattern, which decouples abstraction from implementation for greater flexibility. Additionally, we covered the composite pattern, which allows for the creation of tree structures to manage hierarchies uniformly. The decorator pattern was explained as a way to add behaviors to individual objects at runtime, and the facade pattern simplifies complex subsystem interactions with a single interface. These patterns enhance code maintainability and clarity, providing standardized solutions to common design challenges. Now we will delve deeper into the adapter pattern, explore its implementation in Java, and demonstrate how it can improve your code's flexibility and usability. Now let's take a look at the interfaces we defined for our media application. We have two separate interfaces, video player and audio player. The video player interface declares a method, playVideo, which expects a file name as a parameter to initiate video playback. Similarly, the audio player interface has its own method, playAudio, designed to handle audio files. This separation allows us to create distinct functionalities for audio and video playback. Next, we will implement the simple audio player class, which adheres to the audio player interface. This class will define how to play audio files. With this implementation, we have a concrete class ready to handle audio playback, but now we need a way to adapt this audio functionality so that it can also be treated as a video playback option. Thus, we introduce the audio player adapter. This adapter implements the video player interface and holds an instance of the audio player. The core function of the adapter is found in its playVideo method, where it informs that audio playback is being adapted for video, while internally calling the playAudio method. This allows us to bridge the gap between incompatible interfaces while keeping our audio functionality intact. Next, we will implement a concrete class that adheres to the audio player interface, allowing us to play audio files. We define the simple audio player class, which features a method called playAudio. This method takes a file name as an argument and outputs a message indicating that the audio is being played. By encapsulating the audio playing functionality within this class, we create a straightforward implementation of the audio player interface that can be used in our application. Now let's see how we can enhance the utility of our simple audio player by creating an adapter class, audio player adapter, that enables it to fulfill the role of a video player. This adapter class takes an instance of audio player as a constructor parameter, allowing it to wrap around an existing audio player object. Within this class, we implement the playVideo method, which does not actually play a video. Instead, it informs users that it is adapting audio content and calls the underlying playAudio method, thus preserving the original audio functionality while conforming to the video player interface. This approach effectively demonstrates how the adapter pattern facilitates compatibility between disparate interfaces. Now let's see how we can implement the media app that leverages our audio player adapter for audio playback. In this class, we define the playMedia method, which takes a video player interface and a file name as parameters. This design allows us to treat different types of media players uniformly, whether they are traditional video players or our new audio player adapter. Next, we'll implement the main method. Here, an instance of media app is created and we prepare to adapt the functionality of the audio player. A simple audio player object is instantiated, followed by creating an audio player adapter using the audio player instance. This adapter allows the audio player to be treated as a video player, demonstrating the core advantage of the adapter pattern. Finally, we call the playMedia method with the audio adapter and specify the audio file, song, MP3. This central line exemplifies the seamless integration of audio playback in a video-centric application, showcasing how adapters can bridge differing interfaces and enhance the flexibility of our media playback system without compromising existing functionalities. Now let's implement the payment adapter. which serves as the bridge between our application's payment processing interface and the third-party services method for making payments. The payment adapter class implements the payment processor interface, which defines the process payment method for handling payments. Inside the payment adapter, we maintain a reference to the third-party payment service, enabling us to leverage its payment functionality while adhering to the expected interface of our application. When we invoke the process payment method in the adapter, it seamlessly converts the native method call into the specific make payment method required by the third-party library. Essentially, we provide the necessary currency and amount to the third-party payment service through our adapter, thus ensuring that the underlying service remains encapsulated. This design not only promotes flexibility and adaptability in our payment processing operations, but also maintains the integrity and simplicity of our application code. By employing the adapter, we can easily replace or modify the payment service in the future without necessitating changes to our application's logic. Now let's implement the following example to demonstrate the adapter pattern using a payment processing scenario. Here we have our main class, PaymentApp, which serves as the entry point for the application. Inside the main method, we first instantiate the third-party payment service class, third-party payment service. This class contains the method makePayment, which requires a currency string along with the payment amount, simplifying the interaction with the underlying payment system. Next, we create an instance of payment adapter, passing in the third-party payment service object. The payment adapter implements the payment processor interface and translates its method process payment to meet the expected interface, allowing our application to interact with the payment service seamlessly. In the adapter's process payment method, we call the third-party services make payment method, ensuring all payment processing is done in US dollars. Finally, we call process payment with a specified amount of 100. This illustrates how the adapter enables our application to remain agnostic to the underlying payment services requirements, ensuring flexibility and maintainability in our application's design. The adapter pattern not only simplifies your code, but also reinforces the open-closed principle, suggesting that software entities should be open for extension but closed for modification. By ensuring that your existing code remains unchanged while giving you the ability to introduce new functionality, you create a more robust and flexible design. When implementing the adapter pattern, it is essential to recognize several best practices. Always isolate adapters to keep interfaces clean. Ensure that you create meaningful and coherent adapters, as introducing extraneous adapters can lead to increased complexity. Proper naming conventions can also help convey the purpose of the adapter, making your codebase more understandable. In conclusion, the adapter pattern serves as a powerful tool in software design, allowing disparate classes to interact seamlessly. It enables the integration of new components without the disruption of existing code and promotes code reuse and flexibility. By employing this pattern, you not only enhance the maintainability of your software, but also create a more robust structure that can adapt to future requirements. With the understanding of how to implement and leverage the adapter pattern effectively, you'll be better equipped to handle complex system integrations and foster innovative solutions. As you move forward in your software development journey, consider the adapter pattern as a go-to strategy when faced with incompatible interfaces, and enjoy the newfound flexibility in your code. The composite pattern is a powerful structural design pattern that allows you to treat individual objects and compositions of objects uniformly. It is particularly useful when you need to work with tree-like structures, where both individual items and groups of items need to be handled in the same way. This means you can use this pattern to create complex hierarchies that can be managed in a systematic way. So far, we've learned about the adapter pattern, a structural design pattern that enables incompatible interfaces to communicate by acting as a translator. We explored how it wraps an existing interface to adapt it to a new one, allowing seamless integration in scenarios like media playback and payment processing. The adapter pattern promotes code maintainability and flexibility, adhering to the open-closed principle by enabling extensions without modifying existing code. Now we will cover the composite pattern, examining its implementation and practical applications along with best practices. Now let's take a look at the graphic interface, which lays the groundwork for our composite structure. This interface defines a single method display that all implementing classes must define. This ensures that both the individual shapes and the composite groups will have a consistent way to interact with clients, promoting a unified approach in our design. Next, we will implement concrete classes for our shapes, circle and square, both of which adhere to the graphic interface. In their respective display methods, they provide simple outputs that indicate which shape is being displayed. This straightforward implementation allows clients to invoke display on each shape without needing to know the specifics of the shape's class. Now let's see how we can manage collections of these shapes by introducing the graphic group class. This class is responsible for holding various graphic objects, enabling us to add and remove shapes dynamically. By overriding the display method in graphic group, we can iterate over all contained graphics and call their display methods, effectively showcasing the power of the composite pattern to handle both individual shapes and groups of shapes consistently. This encapsulation significantly simplifies our interactions with complex hierarchies. Now let's implement the graphic group class, which is essential to our composite pattern implementation. This class is designed to hold a collection of graphic objects, allowing us to manage both individual graphics and groups of graphics uniformly. Within the graphic group, we initiate a private list to store the graphics components. The add method is crucial. It enables us to append new graphics to this list, thereby building our group dynamically. Conversely, the remove method provides the capability to delete specific graphics from the group, enhancing our flexibility in managing the collection. Next, we override the display method from the graphic interface. In this implementation, we use a loop to iterate through each graphic stored in our list, calling their own display methods. This approach ensures that when we invoke display on the graphic group, all contained graphics are rendered in a unified manner. Through this class, we effectively leverage the composite pattern, allowing us to add complexity to our graphic structure while maintaining simplicity in how we interact with both individual and composite graphic objects. This structure sets the foundation for creating rich visual compositions, streamlining the rendering process within our graphics application. Now let's implement the following code to demonstrate the functionality of the composite pattern. In this example, we start by creating instances of individual graphic shapes, a circle and a square. These objects adhere to the same interface graphic, which allows them to be treated uniformly within our code. Next, we transition to the concept of grouping graphics by creating a graphic group. This group acts as a container for the circle and square we just created, which we add using the add method. Now we can manage these shapes collectively while still maintaining their individual behaviors. Moving forward, we create a second graphic group called main group, which serves to illustrate the hierarchical nature of the composite pattern. By adding group 1 to main group and also adding another circle directly, we showcase how complex structures can be built. Finally, invoking the display method on main group triggers the display of all graphics, both individual shapes and groups, exhibiting the strength of this pattern in handling varied components uniformly. This encapsulation not only simplifies coding, but also enhances maintainability, empowering developers to effectively manage intricate hierarchies in their applications. The composite pattern has several advantages. First, it allows for the creation of tree structures that can be easily manipulated. Second, it encourages the use of consistent interfaces, which makes the system easier to understand and maintain. Third, changes made at one level of the hierarchy do not typically affect other levels of the hierarchy, promoting flexibility in how the system evolves. However, while the composite pattern has its merits, it also has some drawbacks. Notably, it may lead to complications if misused to create overly complex structures. It's essential to avoid introducing too many layers of composition or allowing design to become unwieldy. Maintaining simplicity and clarity in the design should always be your primary focus. The composite pattern is commonly used in graphical user interface (GUI) frameworks, where components can be composed of other components. Think of buttons, panels, and menus that can all be treated as graphics, allowing for recursive structures and therefore making it easier to manage UI elements together. When implementing the composite pattern, consider a few best practices. Keep the composite structure simple and clear. Avoid making the system overly complex with too many levels of composition. Ensure that your component interfaces are meaningful and that they represent a true part-whole relationship. Regularly test your composite objects to ensure that they behave as expected, especially when it comes to adding or removing components. One common variation of the composite pattern involves the addition of functionality for both leaf nodes and composite nodes. In some cases, it can be beneficial to allow for specific behavior in the components based on whether they are leaf or composite nodes. To do this, you can augment the component interface to include additional methods that only certain objects will implement. However, this can introduce complexity, so keep in mind how it might impact clarity. In summary, the composite pattern is an effective way to treat individual objects and compositions of objects uniformly, allowing you to build flexible and maintainable code. By implementing this pattern, you gain the ability to work with complex structures without compromising the overall simplicity of your code base. Whether you are managing graphics in a GUI framework or any kind of component-based architecture, the composite pattern simplifies the process of interacting with hierarchical structures and enhances your ability to manage them efficiently. As you explore ways to apply this pattern in your projects, lean into its strengths, and remember to prioritize clarity and simplicity in your designs. By mastering the composite pattern, you'll be well equipped to handle complex hierarchies in your software projects and facilitate a more organized and comprehensible code base. Embrace the flexibility it offers, experiment with its applications, and enjoy the newfound power it gives you in your software development toolkit. Now let's take a look at how we implement the front controller pattern using a servlet in Java. We begin by extending the HTTP servlet class with our front controller servlet, which will serve as the single entry point for handling incoming requests. Inside this servlet, we override the doGet method to process the HTTP GET requests. In this method, we first extract an action parameter from the incoming request. Based on this action, we can route the request to specific pages. If the action is login, we forward the request to login.jsp, and similarly, if the action is register, we forward it to register.jsp. For any other action values, we default to directing the user to home.jsp. This routing mechanism consolidates the request handling process, ensuring cleaner and more maintainable code. Next, as we further refine our implementation, we will introduce a command pattern. This enhances the organization of our servlet by mapping specific actions to their corresponding command objects, allowing us to separate the logic for handling each action neatly. This will lead us to a more structured approach, promoting flexibility and reusability in our application. Now let's implement the command pattern by defining a command interface. This interface will serve as a contract for any concrete command classes we create, ensuring they all adhere to a consistent structure. We declare a single method, execute, which takes two parameters, HTTP servlet request and HTTP servlet response. This design will allow us to encapsulate the logic associated with handling different user actions cleanly. Next, we will create specific command classes, namely login command and register command, each implementing the command interface. In the login command, we override the execute method to handle the login logic. Here we can incorporate functionality like user validation and session management. Upon successful login, we forward the request to a success page, maintaining a clean separation from the servlet's core logic. Similarly, the register command class will handle user registration. It too implements the execute method, directing users to a registration success page after processing the necessary registration requirements. This approach provides scalability. Adding new commands for additional actions is straightforward, enhancing maintainability by keeping the front controller servlet focused solely on request dispatching. Next, we will implement the front controller servlet, which exemplifies the adoption of the command pattern for handling incoming requests efficiently. In this servlet, we define a map called command map to store associations between action strings like login and register and their respective command classes. This mapping allows us to streamline request processing and maintain a cleaner code structure. As we proceed to the init method, we populate the command map with instances of our command classes, specifically login command and register command. This setup ensures that when a request is made, the servlet can quickly retrieve the appropriate command based on the action parameter extracted from the incoming HTTP request. Within the doGet method, we check for the action parameter. Instead of cluttering this method with conditional logic for each possible request, we utilize the command map to fetch the corresponding command object seamlessly. If the command exists, it is executed with the provided request and response. Otherwise, we redirect to a default page. This approach not only enhances readability, but also encapsulates specific action logic into distinct command classes, promoting maintainability and separation of concerns in our application design. Now let's implement a logging feature by creating a logging filter class. This class implements the filter interface, allowing it to intercept incoming requests before they reach the front controller servlet. Within the doFilter method, the first action is to cast the incoming servlet request to an HTTP servlet request, which enables us to access HTTP-specific methods. Next, we log the request URI using system.out.println, which provides visibility into the request being processed. After logging, we call the chain_doFilter method to pass the request in response objects to the next filter in the chain or the target servlet if there are no more filters. This ensures that the request flows freely as intended while still adding our logging mechanism. To make this filter operational, we need to configure it in the web XML file. We define the filter's name and class, then map it to a URL pattern such as /, which indicates that this filter should apply to all incoming requests. Thus, every request processed by the front controller will be logged, allowing us to audit user actions without altering the core logic of our servlet or commands. Now that we have examined how to implement the front controller pattern and some of its capabilities, let's discuss its advantages. One significant benefit is the reduction of code duplication. By handling all requests through a single controller, you ensure that common logic is not repeated across multiple servlets. Additionally, centralized management makes it easier to implement cross-cutting concerns such as logging and security filtering, as these can be handled in one place. Another advantage is flexibility. If you need to add new features or modify existing ones, you can do so by updating commands or adding new command classes. This approach is far more manageable than maintaining numerous servlets. Moreover, the front controller can facilitate a cleaner separation of business and presentation logic. By using the command pattern, you can offload business rules and interactions from the servlet itself, keeping it lightweight and focused on request dispatching. However, it's important to consider that implementing a front controller pattern may introduce initial complexity. Setting up the necessary infrastructure, filters, command mappings, and servlet configurations requires more upfront work than simply writing multiple servlets. But the long-term benefits, particularly in large applications, far outweigh this initial hurdle. In conclusion, the front controller pattern is an effective way to manage client request handling in web applications. By centralizing request processing, it simplifies your code, promotes maintainability, and supports the implementation of cross-cutting concerns. You can achieve a cleaner, more organized project structure while maintaining flexibility as your application evolves. As you embark on implementing this pattern in your projects, remember to think carefully about your command design and the responsibilities of your front controller. Properly utilizing this pattern will yield significant improvements in code organization and efficiency. Enjoy your journey into efficient web application development and happy coding. The caching pattern for initialization is an essential technique for optimizing performance in software development. By leveraging previously created elements rather than generating new ones on the fly, applications can save both time and resources. Today, we will delve into how this pattern works, the advantages it offers, and how you can implement it effectively in your own projects. So far, we learned about the front controller pattern, which centralizes request handling in web applications to improve code organization and maintainability. Now we will cover the caching pattern and its role in enhancing application efficiency. Let's begin by understanding what caching actually means in this context. Caching is essentially a method of storing frequently accessed data so that it can be retrieved quickly later without the need to recreate or refetch it every single time. In the caching pattern for initialization, when your application requires an instance of an object, it checks if an instance already exists in the cache. If it does, the application reuses that instance instead of creating a new one. This reduces the overhead associated with initialization and object creation, ultimately leading to improved performance. For instance, imagine a situation where you're building a game. Each time a player creates a character, the game would typically need to initialize that character's stats, abilities, and appearance from scratch. If caching is utilized, the game can retrieve an existing character template from the cache and use that to spawn new characters. This can dramatically speed up the character creation process, especially when there are many players simultaneously creating characters. Now let's take a look at how we can implement the character class and the character factory in Java to demonstrate the caching pattern. The character class represents a character with two properties, name and type, encapsulated through private fields. It provides a constructor for initializing these properties and getter methods to access their values. Next, we will implement the character factory, which plays a crucial role in managing character instances. This factory utilizes a hash map as a cache where characters are stored using a unique key generated from their name and type. The getCharacter method checks if a character already exists in the cache before creating a new instance. If the character is not found, it instantiates a new character, adds it to the cache, and returns it. If the character already exists, the factory retrieves and returns the cached instance. This approach not only optimizes memory usage by reducing instantiation overhead, but also enhances performance by reusing existing objects, a key benefit of the caching pattern in application development. Now let's see how we can implement the main application that utilizes the character factory. In the game class, the main method begins by creating a new instance of the character factory, which will manage our character instances. This factory will enable us to request various characters without directly creating them each time. Next, we create a character named Warrior of type Fighter by calling the factory's getCharacter method. Notably, when we request the same warrior character again, the factory recognizes that an identical instance already exists in its cache and returns the existing character. This is a critical feature, as it demonstrates how the caching pattern improves performance by preventing unnecessary object creation in high-demand scenarios, like those typically found in gaming. We then create additional characters, including a mage and a rogue, and print out their names and types. This not only shows how to retrieve characters from the factory, but also emphasizes how the caching mechanism works to optimize performance, as highlighted by the message that the factory outputs when reusing an instance. This practice significantly enhances resource management within applications. Now let's implement the character class with a crucial clone method to enhance our caching mechanism. The character class begins by defining its properties, such as name and type, which are essential for identifying the character's characteristics. The constructor initializes these fields when a new character is created. Next, we introduce the clone method, which allows us to create new instances of the character based on existing ones. This method uses the current object's properties to instantiate a new character, effectively creating a shallow copy. This capability is particularly important for scenarios where multiple users interact simultaneously with apparently similar characters. By cloning a character instance, we ensure that each player has a unique object that they can modify without affecting other players. Thus, anytime we require an instance of a character, we can request a clone instead of the original instance from our cache. This implementation not only promotes efficient memory usage through caching, but also safeguards against potential side effects from shared state, making our game experience smooth and conflict-free for all players involved. Now let's implement a simple caching mechanism for user profile data using a user profile cache class. This class utilizes a hash map to store user profiles, where each profile is accessed through a unique key composed of the username and email. Within the getUserProfile method, we first construct this key and check if it already exists in the cache. If the key is not found, a new user profile is created and added to the cache, ensuring that we only instantiate new profiles when necessary. This approach significantly reduces the time spent on creating new user profiles by allowing the application to reuse existing instances. It embodies the essence of the caching pattern by enhancing performance and resource efficiency. The use of encapsulation through the user profile class allows us to manage user data effectively, while the cache itself serves as a centralized storage medium that improves response times for frequently accessed profiles. This ensures that user details can be fetched instantly whenever needed, streamlining interactions in web applications. The core takeaway from implementing the caching pattern is that optimizing resource reuse leads to better performance and a smoother user experience. This pattern is hugely advantageous in environments with a high object creation rate, as it minimizes both computation and memory load. As we've discussed, correctly implementing this pattern involves understanding your application's architecture and identifying objects that can benefit from caching. It's imperative to design your caching strategy thoughtfully. Consideration should be given to how long objects need to remain in the cache, when they can be discarded, and how to handle mutability. One will often choose to integrate caching solutions as a layer within an application, facilitating better control over what gets cached and when. This allows developers to specify caching rules around object lifecycle and manage stale data effectively. We have covered the caching pattern for initialization, exploring its principles, advantages, and practical implementations. You should now have a strong understanding of how caching can boost your application's performance and provide a much better user experience. From character creation in games to user profiles in web applications, caching makes it all smoother and faster. Embrace this pattern and your applications will undoubtedly thank you for it. The command pattern is a powerful design pattern that encapsulates a triggered event as an object, allowing the client to act on it more flexibly and dynamically. By organizing commands as objects, we gain the ability to easily parameterize clients with different requests, queue or log requests, and support undoable operations. Today, we'll dive deeper into this pattern, exploring its benefits and how you can implement it in your applications. So far, we've learned about the caching pattern for initialization, which optimizes performance by reusing existing object instances rather than creating new ones. This technique can dramatically reduce overhead and improve efficiency, particularly in resource-intensive applications like games and web services. Examples were provided including a character factory and user profile caching to illustrate how this pattern can streamline object creation and promote better resource management. Overall, understanding and implementing caching can significantly enhance the performance and user experience of your applications. Now we will talk about the command pattern for event handling. Now let's see how we can implement a common interface for our command actions. The command interface defines a single method called execute, which every command will implement. This method serves as the core functionality that subclasses will provide, allowing different commands to be executed depending on the specific action intended. By establishing this interface, we are laying the groundwork for a flexible and extensible command structure. Every concrete command will implement this interface to perform its designated task, ensuring a uniform approach across various commands while encouraging the separation of concerns within our application. This design not only promotes a clear contract for command behavior, but also enables easier modification and expansion of command-related functionalities in the future. Next, we will write the following code defining our concrete command for saving documents within the text editor. First, we create the text editor class, which encompasses the core functionality for document management. It includes a method called save, which outputs a simple message indicating the document has been successfully saved. This class serves as our receiver, the object responsible for executing the actual save action. Now let's implement the save command class, which adheres to the command interface. The save command constructor takes an instance of text editor, effectively binding the command to the specific editor instance. The strength of this implementation lies in its decoupling. The command itself does not know how the action is performed, it simply invokes the execute method, which in turn calls the save method on the text editor. This structure allows the command to operate independently of the interface, making it easy to modify or extend functionality without altering the underlying operations of the text editor. By encapsulating the action in a command object, we gain flexibility in managing various user interactions seamlessly. Now that we have our command set up, we need an invoker responsible for triggering these commands. Next, we will write the button class, which acts as an invoker in our command pattern implementation. This class has a private field for storing a command object and methods for setting that command and simulating a button click. The method set command allows us to dynamically assign a command to the button, enabling flexibility in the command execution associated with the button press. When the click method is invoked, it checks whether a command has been set. If so, it calls the execute method on the command object. This structure allows us to maintain a clean separation between the user interface and the underlying functionality, embodying the essence of the command pattern by decoupling the action from the invoker. Now let's implement the main application, where we will create an instance of text editor, encapsulate the save action in a save command, and link it to our button. By doing this, we streamline how commands are executed within our application, demonstrating the power and flexibility of the command pattern in user event handling. Now let's implement the command interface to include an undo method alongside the existing execute method. This update will allow our commands to not only perform an action but also to reverse it if necessary. With this change, any command that implements this interface will be required to support both execution and undo functionality, enhancing our command pattern's robustness. Next, we will take a look at how to modify the text editor class. This class will now maintain a history of actions via a list to facilitate the undo functionality. When the save method is called, it adds a message to the history before printing a confirmation. The new undo method checks if there's any action in history to reverse, and if present, removes the lost action while notifying the user. Simultaneously, the save command class will be updated to implement the undo method. This ties the command directly to the text editor's undo capability, ensuring that executing and reversing commands remains cohesive and intuitive for users. This approach effectively allows for better management of actions, making the application more flexible in handling user requests. Next, we will write the invoker class, which is crucial for managing command execution and enabling undo functionality. This class maintains a stack to keep track of the commands executed by the user. The execute command method takes a command as an argument, executes it, and then pushes it onto the command stack, ensuring that we have a history of actions performed. This is essential for implementing the undo feature, as it allows us to reverse the lost action taken. Now let's implement the undo command method. This method checks if there are any commands present in the stack. If the stack is not empty, it pops the lost command off the stack and calls its undo method, effectively reverting the previous action. If the stack is empty, it informs the user that there are no commands to undo, enhancing user experience by providing clear feedback. Finally, we will integrate our various components in the command pattern with undo example class. In this main application, we create an instance of the text editor and a save command. Using the invoker, we can execute the save command and demonstrate the undo operation. This seamless handling of commands showcases the flexibility and organization the command pattern brings to our applications. Now let's implement the logging functionality using a decorator pattern called logging command. This class takes an existing command as an argument and wraps it. By doing so, it enhances the command's capabilities without modifying its original behavior. The constructor accepts a command object stored in the wrapped command variable. When the execute method is called, it first prints a log message indicating that the command is being executed. The name of the command being executed is dynamically retrieved using reflection, ensuring the log remains accurate regardless of which command is wrapped. After logging, it delegates the execution to the wrapped command, allowing the original command's functionality to occur. Similarly, the undo method works in tandem with the execute method. It logs a message stating which command is being undone before calling the undo method of the wrapped command. This approach provides a clear audit trail for actions performed, facilitating debugging and enhancing the ability to track user interactions in the application. This logging mechanism not only organizes our operations but also adds transparency to user actions, improving overall code maintainability. To conclude, the command pattern is an immensely valuable design pattern for structuring event handling in your applications. By encapsulating requests as objects, you create a scalable solution that can handle various requirements, from command queuing to undo functionality and logging. The ability to decouple the sender from the receiver makes it easier to manage complex behavior in your code, leading to better organization and maintenance. In today's session, we've explored how to implement the command pattern in Java with practical examples. We started with a simple text editor and then extended functionality to include undo operations, command logging, and demonstrated how components interact smoothly. As you move forward, consider how integrating the command pattern can enhance your projects by making them more extensible and easier to manage. Thank you for joining this tutorial. Dive into your coding and remember, your commands can be powerful tools in designing intricate and user-friendly applications. Happy coding! The state pattern is a vital design concept that facilitates behavior change in objects based on their internal states. It allows an object's behavior to vary with its state, enabling more dynamic and adaptable applications. Today, we will delve into the fascinating world of the state pattern, exploring how it can be effectively implemented and the advantages it offers. So far, we learned about the command pattern, which encapsulates requests as objects to enable flexible and dynamic event handling. This pattern decouples the sender from the receiver, making it possible to implement features like queuing, undo operations, and logging actions. We explored a practical implementation in Java with a text editor application, showcasing how to execute and undo commands effectively. The command pattern significantly enhances code organization and facilitates the management of complex behaviors in applications. Now we will talk about the state pattern, focusing on how it can influence an object's internal processes based on the mutation of its internal state. Now let's take a look at the state interface, which is a foundational component in implementing the state pattern for our media player. This interface defines three essential methods: play, pause, and stop. Each of these methods will be overridden by the concrete state classes that represent different states of the media player. By encapsulating these behaviors into the interface, we ensure that every state class will provide its own implementation of how these actions should be handled based on the current state of the media player. Next, we will implement the specific states: playing state, pause state, and stop state. Each class will maintain a reference to the media player instance, allowing them to change the player's state seamlessly. For example, in the playing state, the play method will simply notify the user that the player is already active, whereas a call to pause will transition the media player to pause state. This organization allows us to separate state-specific behavior cleanly and makes the code easier to maintain and extend. Let's now examine the media player class, which serves as the context for managing our states. This class holds instances of each state and keeps track of the current state with the current state variable. The play, pause, and stop methods directly delegate these operations to the current state object. This setup allows for dynamic behavior modification as the user interacts with the media player, demonstrating a clear practical application of the state pattern. Next, we will create our concrete states: playing state, pause state, and stop state. Each of these classes will implement the state interface and provide specific behavior for the media player's state. Starting with the playing state, we see that it holds a reference to the media player instance. When the play method is invoked in this state, it informs the user that the media is already playing. The pause method allows the media player to transition to the pause state, while the stop method transitions it to the stop state, encapsulating the logic that belongs to the playing state. Moving on to pause state, this class also holds a reference to the media player. Here, invoking play resumes playback and transitions back to the playing state, whereas calling pause simply indicates that the media is already paused. The stop method, like before, changes the state to stop state. Lastly, in the stop state, the behavior is straightforward. When play is called, it starts playback and transitions to playing state. However, if pause is called while stopped, it will prompt the user to play first, ensuring users understand the player's status. The stop method simply confirms that the media is already stopped. This structure allows for a clear and extensible design, adhering to the principles of the state pattern. Now let's take a look at the media player class, which plays a pivotal role in managing the states of our media player and their interactions. In this class, we define private instances for each state: playing state, pause state, and stop state, along with a current state that keeps track of the player's active state. We initialize these states in the constructor, setting the initial state to stop state, indicating that the player starts off non-active. Next, we have a set state method that allows us to change the current state dynamically, enhancing the player's ability to adapt based on user interaction. Additionally, we provide getter methods for each state, which will be utilized by the state classes to switch between the various states. The play, pause, and stop methods delegate the calls to the current state, meaning that each state can define how these actions are handled. This delegation eliminates the need for cumbersome conditional statements and allows each state to encapsulate its specific behavior, making the code more modular and maintainable. Overall, this structure embodies the essence of the state pattern, simplifying state management while enhancing code organization. Now let's bring everything together in our main class, which serves as the entry point for our media player application. In this class, we first create an instance of the media player, initializing it in the stop state. Next, we can observe how the media player's behavior changes dynamically as we interact with it. For instance, when we call the play method, the media player transitions from the stop state to the playing state, triggering the corresponding behavior defined in the playing state class. Similarly, invoking the pause method allows our media player to pause playback, changing its state to pause state as per the logic we structured. We can also resume playback by calling play again, which reflects its current state. Finally, when we call stop, the media player correctly transitions to the stop state. Notably, trying to pause the player while it's already stopped demonstrates the effectiveness of our state pattern, where behaviors are encapsulated based on the current state, eliminating the need for complex conditional logic. This encapsulation not only simplifies our codebase, but it also enhances maintainability and scalability, making our application more adaptable to future changes. The state pattern brings significant advantages to our media player. First, it greatly simplifies our code, keeping the behaviors associated with each state together. This modular design makes it easy to add or modify states without altering the overall functionality of the media player. For example, if you wanted to add a new rewind state, you would simply implement another class based on the state interface and set up transitions accordingly without having to touch the core application logic. Moreover, it enhances the maintainability of the code. If there's an issue related to a certain state, you can pinpoint your changes to that specific class. This isolation of functionality fosters a better understanding of where specific behavior resides, making debugging simpler and more efficient. Another key benefit of the state pattern is how it enables an object to change its behavior at runtime. In our media player, as various user interactions occur, the media player actively modifies its state, which in turn influences how it processes requests. This dynamic capacity to adapt behavior aligns well with systems that require responsiveness to varying contexts, such as game development or even complex software that interacts with multiple user input types. To summarize, the state pattern not only provides a clean way to manage various states of an object, but also results in a more vibrant, responsive application. The separation of states into unique classes paves the way for easier scaling and feature integrations, which could be a game changer for your development workflow. In closing, today we've discussed the state pattern in detail, showcased practical implementations in a media player context, and explored its significant advantages. By encapsulating state-specific behavior within dedicated classes, we enhance the adaptability, maintainability, and readability of our code. Next time you're designing a system with varying behaviors, consider implementing the state pattern to take your applications to the next level. Thank you for tuning in, and until next time, keep coding and exploring new design patterns that make your applications shine. The visitor pattern is a powerful design pattern that enables the separation of algorithm execution from the objects it operates on. This allows you to add new operations to existing object structures without modifying the objects themselves. It's like having a service that can go through your home and inspect everything without changing the furniture. So far, we learned about the state pattern, which allows an object's behavior to change based on its internal state, enabling more dynamic applications. We explored its implementation through a media player example where different states like playing, paused, and stopped are managed via separate classes. This design reduces complexity, enhances code maintainability, and allows for easy extensions like adding new states. Ultimately, the state pattern fosters adaptable and responsive applications that can better handle various user inputs. Now we will talk about the visitor pattern, delving into how it can help us execute operations on objects without altering their structures. Now let's take a look at the cornerstone of our visitor pattern implementation, which begins with the definition of the shape interface. This interface establishes a contract that all geometric shapes must adhere to, defining a single method, except which takes a shape visitor as a parameter. This design allows each shape to process different types of visitors without altering their own implementations, promoting the pattern's core principle of decoupling operations from the objects. Next, we will write the concrete shape classes: circle, square, and triangle. Each of these will implement the shape interface, ensuring they all provide the necessary accept method. This method is crucial as it enables the visitor to interact with the specific shape instance, invoking the appropriate operation defined in the visitor. By following this structure, we maintain a clean separation of concerns, allowing the shapes themselves to remain focused on their attributes while delegating operational behavior to the visitors. This setup sets the stage for a flexible system, where we can easily introduce new operation types without modifying existing shapes, effectively adhering to the open-closed principle of software design. Next, we will implement the concrete shape classes: circle, square, and triangle, which will adhere to the shape interface we defined earlier. Each class will encapsulate its unique attributes, such as radius for the circle, side length for the square, and base and height for the triangle. In each of these classes, we have a constructor that initializes these properties and corresponding getter methods to retrieve their dimensions. A key feature of these classes is the accept method, which plays a critical role in the visitor pattern. This method takes a shape visitor as an argument and invokes the visit method on the visitor, passing the current shape instance. This design allows the visitor to process shape-specific operations without altering the shape classes themselves. By implementing the accept method in each shape, we ensure that any new operation can be added through visitor classes while keeping the structure of our shapes intact. This approach promotes flexibility and adheres to the open-closed principle, making it easy to introduce additional operations without modifying existing code. Now let's create our visitor interface by defining the shape visitor, which serves as a contract for different visitor implementations. This interface outlines the visit methods that will handle various shape types, specifically for circle, square, and triangle. By doing this, we ensure that every concrete visitor implementing this interface must provide specific behavior for each shape type, promoting consistency in operations. Next, we will implement the area calculator class, which is a concrete visitor that performs area calculations for each shape. Within this class, we override the visit methods to define the logic for calculating areas. For the circle, we apply the formula \pi times r2 using the circle's radius. For the square, it's simply the side length squared, while for the triangle, we use the formula \0, 5 times text base times text height . This structure demonstrates the visitor pattern strength, allowing us to define new operations without changing the original shape classes. Each visit method encapsulates the behavior specific to each shape, showcasing how easily we can augment our system with new functionalities simply by creating new visitors that adhere to the established interface. Now let's implement the following main class to bring our visitor pattern to life. In this example, we create an array of different shapes, including instances of circle, square, and triangle, each initialized with specific dimensions. This setup allows us to encapsulate the different geometric shapes in an easily manageable structure. We then instantiate our area calculator, which serves as our visitor that will perform operations on the shapes. Next, we employ a for loop to iterate through each shape in the array. For every shape, we invoke its accept method, passing our area calculator as an argument. This method call is crucial because it delegates the responsibility of area calculation to the visitor, which then invokes the specific visit method tailored to each shape type. This design highlights the power of the visitor pattern, enabling us to easily compute the area of various shapes without altering their individual classes. This separation of responsibilities keeps our code clean and adheres to the open-closed principle, ensuring that our shape classes remain unchanged as we introduce new functionalities. Now let's implement the perimeter calculation for our shapes using the visitor pattern. We begin by creating a new class called Perimeter Calculator, which implements the Shape Visitor interface. This class will contain the methods necessary for calculating the perimeter of each shape type. Within Perimeter Calculator, we override the visit methods for circle, square, and triangle. For the circle, we use the formula \2 times pi times text radius to compute the perimeter and print the result. Similarly, for the square, the perimeter is simply \4 times text side \. In the case of the triangle, we can provide a rough estimate of the perimeter by summing the base, height, and an arbitrary side length. This highlights how the visitor pattern allows us to introduce new functionalities without modifying the existing shape classes. By keeping the perimeter logic encapsulated within the perimeter calculator, we adhere to the open-closed principle, enhancing code maintainability. If we need to add more calculations down the line, we can simply create additional visitor classes without touching the shape implementations, demonstrating the true power and flexibility of the visitor pattern. Another compelling advantage of the visitor pattern is the clear separation of concerns. It helps maintain a clean code structure. Since operations are encapsulated within visitor classes, the responsibilities of the object structures remain intact while new functionalities can be layered in seamlessly. Also, think about how your code is easier to maintain and evolve. If any bugs occur or additional features are required, the visitor pattern delineates where changes need to occur, which typically resides within the visitor class rather than entangled within each data structure. Now let's implement the rectangle class as part of our shape structure. In this code, we define the class rectangle that implements the shape interface, adhering to the visitor pattern principles we've established. The rectangle class includes two private member variables, width and height, which represent the dimensions of the rectangle. To initialize these properties, we create a constructor that sets the width and height values when a new rectangle object is instantiated. This encapsulation ensures that the dimensions of our rectangle are only accessible within the class, maintaining the integrity of the shape's data. Next, we provide two public methods, getWidth and getHeight, which allow external classes to retrieve the rectangle's dimensions without modifying them. This is a critical aspect of object-oriented design, promoting data hiding. Moreover, we implement the accept method required by the shape interface. This method takes a shape visitor as a parameter and calls the visitor's visit method specific to the rectangle class. By doing this, we ensure that our rectangle can be processed by any visitor, making it easy to extend our capabilities without altering the rectangle's internal structure. In conclusion, the visitor pattern is not just a clever trick. It's a robust design approach to separating algorithms from the objects they operate on. By utilizing the visitor pattern, we enhance the flexibility of our applications, ensuring that adding new behaviors or operations can be done with minimal fuss. The clear structure resulting from this design also fosters better maintainability and readability, allowing developers to focus on functionality without losing sight of their organization. If you find yourself constantly adding new operations to a complex object structure, or if you've got an object hierarchy that's growing more convoluted by the day, think about incorporating the visitor pattern into your design toolkit. It's an excellent way to keep things organized and manageable while letting your creativity shine through with new functionalities. And as you dive deeper into the world of design patterns, remember that each pattern serves a unique purpose. Learning how and when to use them effectively makes you not just a coder but a true software craftsman. Thank you for tuning in to this tutorial. Until next time, keep exploring, stay curious, and happy coding. The active object design pattern is a powerful concept in software architecture that emphasizes the separation of method execution from method invocation, enabling a smoother execution of concurrent processes. This pattern is particularly useful in situations requiring responsiveness and resource management, allowing developers to create applications that efficiently handle multiple tasks simultaneously. So far, we learned about the visitor pattern, which separates algorithm execution from the objects it interacts with, allowing for new operations without altering the existing object structures. We discussed its application through a geometric shapes example and the implementation of the shape interface, where different shapes like circle, square, and triangle accept a visitor for various operations. The visitor pattern enhances code flexibility and maintainability, allowing easy addition of new functionalities without modifying existing classes. Finally, we acknowledge the potential complexity in adding new elements, highlighting a trade-off between operation expansion and structural stability. Now we will talk about the active object design pattern and how it can help create responsive and maintainable applications. In the active object design pattern, the focus is on wrapper classes that encapsulate the asynchronous execution of method calls. This allows us to decouple the actual processing from the immediate invocation, typically achieved by running a control thread dedicated to processing these method calls. The concept is akin to having a waiter take your order in a restaurant. The waiter active object takes multiple orders and processes them in the background without making you wait at the table. The primary benefit of this approach is that it enhances system responsiveness, especially in applications that require multitasking or need to manage heavy loads of operations like server applications or graphical user interfaces (GUIs). By allowing the active object to process requests in its control thread, the main thread remains unblocked, leading to a more responsive user experience. Now let's take a look at the implementation of our ActiveShape class, which enables asynchronous drawing operations. The first step in our code is to import necessary classes from the Java util concurrent package, specifically blocking queue and link blocking queue, which we will use to manage method calls in a thread-safe manner. Inside the class, we define a blocking queue to hold runnable tasks, representing the shape drawing requests. We also establish a dedicated thread, known as the control thread, which continuously processes these queued tasks. In the constructor, we initialize the blocking queue and start our control thread. The thread operates in a loop, retrieving tasks from the queue using the take method, which blocks until a task is available. Once a task is retrieved, it is executed using run. Next, we implement the drawShape method, which allows users to request a shape to be drawn. Instead of executing the drawing operation immediately, this method places a runnable task into the queue. This non-blocking approach enables the main application thread, such as a GUI, to remain responsive, accepting further user inputs without delay. Lastly, we include a close method to safely shut down the control thread when our active object is no longer needed, ensuring a graceful termination of the process. Now let's see how we can implement a simple GUI application that utilizes our ActiveShape class to allow users to draw shapes interactively. The application begins by instantiating the ActiveShape object, which will manage the asynchronous drawing operations. We then create a JFrame to serve as the main window of the application and add two buttons, one for drawing a circle and another for drawing a square. Next, we attach action listeners to these buttons. When the Draw Circle button is clicked, the associated action listener calls the drawShape method of our active object, passing circle as an argument. This action places the drawing request into the method queue for the ActiveShape class to process. Similarly, clicking the Draw Square button triggers another action listener that performs the same operation but with square. The layout is configured using Flow Layout to make the buttons appear side by side in the frame. Finally, we set the size of the window, define its close operation, and make it visible. Through this design, the application showcases how the active object pattern keeps the GUI responsive, even as drawing operations are processed in the background. Now let's see how we can enhance our ActiveShape class to improve error handling within the active object pattern. We begin by implementing an inner try-catch block around the method call execution. This modification allows us to catch any exceptions that may occur during the processing of method calls. If an error occurs, an informative error message is printed, indicating the nature of the error without crashing the application. By centralizing exception handling within the control thread, we maintain a clear separation of concerns, ensuring the rest of the application remains unaffected by these internal errors. This structured error management is a significant advantage of using the active object pattern, as it promotes robustness and stability in applications. Thus, when we invoke methods on our ActiveShape, any issues arising during their execution are properly managed, allowing the application to handle problems gracefully. This enhancement not only leads to a more resilient system, but also improves the overall user experience by preventing unexpected crashes and providing useful feedback when something goes wrong. Now let's implement a mechanism within our ActiveShape class that allows us to control the number of concurrent tasks being processed. This is achieved by introducing a semaphore that regulates access to the processing part of our active object. In this code, we create a semaphore which takes an integer parameter, max concurrent processes, This parameter defines the maximum number of tasks that can be executed simultaneously. Next, we initialize a blocking queue to hold the method calls, thereby ensuring that no method call is lost while waiting to be processed. The core functionality is handled in the control thread, which continuously retrieves tasks from the queue. Before executing each method call, the control thread attempts to acquire permit from the semaphore. This enforcement guarantees that only a limited number of tasks run concurrently, preventing resource exhaustion and ensuring controlled load management. Once a task is executed, regardless of success or failure, the permit is released, making it available for subsequent tasks. This structured flow not only improves performance tuning, but also maintains system stability during high-load scenarios, highlighting the advantages of using the active object pattern effectively. While the active object design pattern comes with its advantages, it's essential to recognize potential pitfalls. Implementing and maintaining an active object requires careful synchronization and management of the lifecycle. Developers should be cautious with resource management, ensuring that threads are gracefully shut down when no longer needed, which can help to avoid memory leaks or resource contention. It is also vital when designing APIs that utilize active objects to document expected behaviors and any potential blocking characteristics, as this can greatly influence how clients interact with the API. Documentation and clear expectations can prevent misuse and enhance user experience. In summary, the active object design pattern is a fascinating and useful technique for creating robust, responsive applications that can handle multiple tasks efficiently. By encapsulating method invocation and execution into separate threads, we enhance system responsiveness and maintainability. Through the examples we've discussed, we've seen how to create an active shape class to manage drawing shapes in an asynchronous manner while keeping the UI interactive. We've looked at error handling and performance tuning mechanisms, ensuring our applications can handle exceptions gracefully and manage resources effectively. With a proper understanding of this pattern, you have the tools to build applications that can respond to user input without delay, resulting in a better overall user experience. So now, the next time you're faced with a challenge that involves concurrent processing, consider leveraging the active object design pattern to create a snappier and more efficient application. Thanks for joining me today, and happy coding. The double-checked locking pattern solves the problem of an application requiring only one instance of a particular class at runtime. In simpler terms, it's a method used to safely create and access a single instance of a class, commonly referred to as a singleton in a multi-threaded environment. This pattern aims to improve the performance of instance creation while ensuring that no multiple threads create multiple instances at the same time. So far, we covered active object design patterns that focused on the separation of method execution from invocation to enhance system responsiveness and resource management. We explored an implementation of the active shape class that improved the interactivity of user applications. Now we will delve into the double-checked locking pattern, discussing its implementation in Java and exploring how it can help efficiently manage singletons in a multi-threaded environment. Now let's implement the double-checked locking pattern in our singleton class. The class starts by defining a private static variable named instance, declared as volatile. This keyword is essential because it ensures that the instance variable is always accessed directly from the main memory, preventing threads from caching it in a way that could lead to visibility issues or partially constructed instances. Next, we create a private constructor for the singleton class. This restricts instantiation from outside the class, aligning with the singleton design principle of having only one instance. Moving to the getInstance method, we first check if instance is null. This is the first check, and if it is null, we enter synchronized block, which ensures that only one thread can execute the section at a time. Within this block, we perform a second check to see if instance is still null. This step is vital because it guarantees that we only create a new instance if none exists, thereby minimizing performance costs. If both checks confirm that the instance is null, we proceed to create a new singleton object. Once done, this method returns the single instance, allowing for efficient access throughout a multi-threaded environment. Now let's break down the code. The private constructor prevents external classes from instantiating the singleton class directly. The getInstance method first checks if the instance variable is null. If it is, we enter a synchronized block to ensure that only one thread can access this section of the code at a time. This is where the locking happens. Once inside the synchronized block, we check again if the instance is null. This second check is crucial because even if one thread has passed the first check, another thread could have already created the instance once it entered the synchronized block. If it's still null, we create a new instance of the singleton class. This two-step process ensures that we only incur the performance cost of synchronization if the instance is actually created, as subsequent calls to getInstance will immediately return the already created instance without synchronization overhead. Now let's implement the following logging singleton using the double-checked locking pattern. In this implementation, the logger class is designed to maintain a single instance of itself throughout the application lifecycle. This is crucial for ensuring consistent log outputs across different parts of a multi-threaded application. The class begins with a private static volatile variable named instance. The volatile keyword plays a vital role here, ensuring that when the instance is accessed, it reflects the most recent assignment made by any thread, preventing subtle concurrency issues. The constructor of the logger is private, which prevents any external classes from creating new instances, thus enforcing the singleton property. The main method of interest is getInstance, which is responsible for providing the global access point to the logger instance. Within this method, we first check if instance is null. If it is, we need to synchronize access to create the instance. This is where double-checked locking comes in. After acquiring the lock, we perform another check to ensure that no other thread has already created an instance. Only if it is still null do we create a new logger instance. Finally, the log method is provided for logging messages, ensuring all logs originate from the same logger instance, thus maintaining consistency in the application's logging mechanism. Now let's see how we can implement an enum singleton, which is a straightforward and thread-safe approach to creating a singleton in Java. The configuration enum declares a single instance, which is automatically instantiated by the Java Virtual Machine JVM. This eliminates any concerns regarding synchronization and thread safety. Inside the enum, we have a private field called config setting that stores configuration settings. To manipulate this setting, we provide two methods: setConfig, which allows the user to assign a new value to config setting, and getConfig, which retrieves the current value. This straightforward design encapsulates all the necessary behavior and state management within the singleton instance. When you call configuration instance, you're guaranteed to access the one and only instance of configuration, ensuring that no duplicate instances are created and simplifying the overall state management in your application. This method of using enums is not only concise but also inherently protects against serialization issues that can arise with singletons, making it a robust alternative to traditional singleton patterns like the double-checked locking. Now let's implement the initialization on-demand holder idiom for our singleton pattern. In this design, we start with a private constructor for the database connection class, which prevents external instantiation and enforces the singleton principle. Next, we create a static nested class named holder. This holder class contains a static final instance of database connection, ensuring that the instance is created only when it's first accessed. By leveraging the class loaders mechanism, this approach guarantees that the instance will be initialized only when the getInstance method is called for the first time. This lazy initialization is both efficient and thread-safe without the complexity of explicit synchronization. The getInstance method simply returns the instance from the holder class. Since the outer class does not need to manage the lifecycle of the instance directly, it simplifies the code structure and avoids potential threading issues. Overall, this pattern elegantly balances performance and simplicity while effectively implementing a singleton in a multi-threaded environment. In conclusion, the double-checked locking pattern offers an effective way to implement the singleton pattern while ensuring thread safety and minimizing unnecessary performance costs. However, it's crucial to approach its implementation with caution, understanding how volatile fields and synchronization work in Java. By ensuring you have a firm grasp of concurrency principles, you can use double-checked locking effectively in your projects. We also explored alternative implementations, such as enum singletons and the initialization on-demand holder idiom, each with their own advantages and particular use cases. As we move forward, it's important to continue discussing best practices and patterns that enhance the robustness of your applications. Thanks for joining me in this exploration of the double-checked locking pattern, and happy coding. Now let's implement a shared resource class that effectively utilizes the reentrant read-write lock to manage concurrent reading and writing operations. This class begins by initializing a reentrant read-write lock instance, which allows us to differentiate between read and write access to the shared resource shared data. The read method showcases how we can safely allow multiple threads to read the data concurrently. It acquires a read lock before accessing shared data, ensuring that while one or more threads have the read lock, no writes can occur, thus maintaining data consistency. Conversely, the write method uses a write lock, which guarantees that only a single thread can write to shared data at any given time. If a thread holds this lock, all other threads are blocked from both reading and writing until the lock is released. This exclusive access is critical to uphold data integrity, especially during modification. With this structure, we can efficiently manage threads, interactions with shared data, allowing for improved performance in multi-threaded environments where read operations significantly outnumber writes. Now let's see how we can enhance the write method to handle scenarios where acquiring the write lock may take longer than expected. In this implementation, we utilize try-lock with a specified timeout set to 1 second in this case. The method initially tries to acquire the write lock for that duration. Within the try block, we check whether the write lock was successfully acquired. If it is, the method proceeds to write the new data into the shared resource. However, if acquiring the lock fails within the timeout, the method prints a message indicating that the write lock wasn't obtained and suggests trying again later. This approach prevents the thread from blocking indefinitely, thus improving the system's overall responsiveness under contention. Moreover, the method also includes error handling for any interruptions, ensuring that if the thread is interrupted while waiting for the lock, it will restore its interrupted status. Lastly, the finally block ensures that if the write lock was successfully acquired, it will be released, maintaining proper lock management and preventing potential deadlocks. This thoughtful construction of the method reflects a proactive strategy for managing concurrency and enhances the system's reliability. Now let's take a look at the implementation of our userProfilCache class, which effectively demonstrates the use of read-write locks in a concurrent environment. This class utilizes a concurrent hash map to store user profile data, allowing for efficient retrieval and updates without the risk of data corruption. Next, we will define the getProfile method, which is designed to read user profiles. This method acquires a read lock before accessing the user cache. By obtaining this lock, it ensures that multiple threads can access this method simultaneously without blocking each other, thus enhancing performance during read operations. The lock is released in a finally block to guarantee that it is freed, even if an exception occurs. Now let's implement the updateProfile method, which is responsible for updating user profile data. This method acquires a write lock prior to making any modifications. The write lock ensures exclusive access, allowing only one thread to update the profile at a time. This mechanism protects the integrity of the user data during concurrent modifications, ensuring safe updates while still benefiting from the performance advances provided by the read-write locking strategy. However, like any pattern, the read-write lock has its trade-offs. Developers need to weigh the complexity it introduces against the expected performance improvements. While read-write locks can significantly increase performance in read-heavy scenarios, they can also introduce complexities in debugging and design. Moreover, in systems where writes are more frequent than reads, the overhead of managing multiple locks can outweigh the benefits. An essential consideration in implementing read-write locking is to ensure that your application is truly read-intensive. In cases where read and write operations are balanced, a standard lock might suffice, simplifying development and maintenance. Another factor to think about is the potential for deadlocks, which can occur if not managed properly. Make sure to have clear strategies in place to prevent deadlocks from happening, such as avoiding nested locks or ensuring a consistent lock acquisition order across threads. To highlight the appropriate use cases further, let's compare a few scenarios. For databases where data retrieval is much more frequent than data modification, implementing read-write locks can lead to substantial performance improvement. However, in systems that require high reliability and consistency, such as financial transactions, the use of read-write locks may introduce too much complexity and risk. In summary, the read-write locking pattern introduces an efficient way to manage concurrency when dealing with shared resources. By allowing multiple threads to read simultaneously while ensuring exclusive access for write operations, this pattern helps optimize performance in read-heavy applications. By utilizing Java's reentrant read-write lock, you can easily structure your code to leverage the benefits of this pattern. Always remember to analyze your specific use case and application requirements to determine whether implementing read-write locks is appropriate. Keeping in mind the concerns of thread contention, lock starvation, and possible deadlocks ensures you create robust, efficient multi-threaded applications that can handle the demands of modern software, giving your users the experience they expect. Thank you for joining this exploration of the read-write lock pattern, and as you continue developing in multi-threaded environments, I hope you find this knowledge useful in enhancing performance and reliability in your projects. The producer-consumer pattern is a common design pattern that enables decoupling of processes that produce data and those that consume it. effectively allowing values to be produced and consumed without blocking the main application thread. This pattern is particularly useful in scenarios where the speed of production might not match the speed of consumption, enabling a smooth flow of data and preventing bottlenecks in applications. So far, we learned about the read-write locking pattern, which optimizes access to shared resources by allowing multiple threads to read simultaneously while ensuring exclusive access for writes. This pattern is particularly effective in scenarios with a high frequency of read operations compared to writes, improving overall performance. We also discussed the implementation of read-write locks in Java using the reentrant read-write lock, and highlighted considerations such as thread contention, lock starvation, and the potential for deadlocks. Understanding these principles is crucial for developing efficient and robust multi-threaded applications. Now we will talk about the producer-consumer pattern, including its implementation in Java and how it can be effectively utilized in real-world applications. Now let's implement the foundational structure for our producer-consumer example in Java. We begin by defining a blocking queue with a specified buffer size of 5, which serves as our shared buffer for produced items. This queue allows for safe interactions between producer and consumer threads as it handles necessary synchronization, ensuring that operations are thread-safe. In the main method, we create two threads, one for the producer and another for the consumer. By instantiating our producer and consumer classes and passing the shared blocking queue to each, we set the stage for concurrent operations. The producer will generate data while the consumer will retrieve this data from the queue. Finally, we start both threads, initiating their execution responses. This setup encapsulates the essence of the producer-consumer pattern, allowing for smooth and efficient data handling without blocking the main application thread. Now let's implement the producer class, which is key to our producer-consumer example. This class implements the runnable interface, allowing instances to be run as a thread. We start by defining a private field queue of type blocking queue integer, which will hold the integers produced. In the constructor, we initialize this queue so that the producer knows where to place the items it generates. The heart of the class is found in the run method, where we use a loop to produce 10 integers sequentially. Each integer is added to the blocking queue using the put method, which ensures that if the queue is full, the producer thread will wait until there's space available. This interaction is crucial for preventing the producer from overwhelming the consumer. We also print a message indicating the integer that has been produced, giving us real-time feedback on the production process. To simulate realistic production timing, we include a thread sleep 500 call, which pauses the thread for half a second between productions. This pacing helps illustrate the flow of data in our application and shows the significance of timing in multi-threaded environments. Additionally, the code includes error handling for interrupted exceptions, allowing for graceful termination of the producer if it's interrupted. Now let's take a look at the consumer class, which is essential for retrieving and processing items from the shared blocking queue. This class implements the runnable interface, allowing us to execute it on a separate thread. In the constructor, we initialize the queue variable, which holds the reference to the blocking queue that will be used for consuming items. The core functionality is found in the run method, where the consumer continuously retrieves 10 integers from the queue. By using the take method, the consumer waits for an item to become available if the queue is empty, effectively synchronizing with the producer. Each integer retrieved is printed to the console, allowing us to track what is being consumed. As a demonstration of a real-world application, we simulate the time it takes to consume an item with a thread sleep 1000 call, which introduces a deliberate delay. This delay helps illustrate the scenario where the consumer is slower than the producer, creating an interesting dynamic in the production-consumption relationship. The use of exception handling for interrupted exception ensures our consumer can gracefully handle disruptions, which is crucial for maintaining stability in multi-threaded applications. Now let's take a look at how we can handle multiple producers and consumers in our implementation. We start by defining a new buffer size of 10, which will allow us to accommodate more produced items before the consumers take them. The blocking queue is implemented using array blocking queue, providing us a thread-safe way to store the produced items. In the main method, we create 3 producer threads and 2 consumer threads. Each producer will continuously generate items, while the consumers will retrieve and process these items concurrently. The threads are started immediately after they are created, allowing them to operate independently. The blocking queue automatically manages the synchronization between these threads, ensuring that data integrity is maintained without the risk of data loss. This structure allows for efficient communication between the producers and consumers. as the blocking nature of the queue means that if the queue is full, producers will be temporarily blocked until space is available, and when the queue is empty, consumers will wait for items to be produced. With multiple producers and consumers, our system can handle a higher throughput, illustrating the flexibility and robustness of the producer-consumer pattern in Java. When using the producer-consumer pattern, developers must consider the system's architecture, including how many producers and consumers should be used. Ideally, if there are many slow consumers, adding more producers may not help as the inhibitors are the consumer's speed. Each system is unique, so monitoring and testing different configurations to find the optimal balance between producers and consumers is crucial. It's also worth mentioning the importance of graceful shutdown in multi-threaded applications. You wouldn't want your producers and consumers to leave resources hanging when the application shuts down. Adding shutdown logic can help ensure threads terminate cleanly without leaving the queue in an unstable state. Furthermore, proper exception handling is vital, as exceptions in any of the threads can affect the entire process. In our implementation, we have catch blocks for interrupted exceptions, ensuring that our threads can exit gracefully if interrupted. To illustrate the broader impact of the producer-consumer pattern, let's consider a few real-world applications beyond just factory lines or web servers. For instance, in logging systems, where log messages can be produced at unpredictable rates, a buffer using the producer-consumer pattern allows efficient handling of logs without losing messages during peak loads. In fintech applications, the pattern helps balance the speed of trading signals generated by algorithms with the speed those signals are processed. This allows for improved throughput and ensures that you aren't losing any critical trade opportunities. Additionally, the producer-consumer pattern is also beneficial in client-server architectures, where clients send requests to a server at varying speeds. The server can queue the incoming requests while processing them at its own pace, ensuring that it does not become overloaded. In conclusion, the producer-consumer pattern is a powerful tool in the realm of multi-threaded applications, providing a mechanism to produce and consume data effectively without causing bottlenecks or overwhelming the system. By using structures like the blocking queue, we can simplify implementation while ensuring thread safety. Armed with this understanding, you can tackle various challenges in your applications, from managing resource allocation efficiently to creating responsive user experiences in server setups. As you delve into your projects, consider how this pattern can be leveraged to enhance performance and reliability, ensuring that producers and consumers can coexist in a harmonious multi-threaded world. Thank you for joining me as we explored the producer-consumer pattern, and remember, happy coding. In software development, an anti-pattern can be clearly defined as the exact opposite of a good design pattern or best practice. While that sounds straightforward, it overlooks the surrounding context and the sequence of events that led to a software practice acquiring the anti-pattern label. This context is crucial to understanding that these anti-patterns are comprised of risky, ineffective, and often counterproductive steps. Recognizing these steps allows us to avoid them as we move forward with our designs and implementations. In this video, we'll explore various anti-patterns, examining both the pitfalls and best practices associated with them. Now let's take a look at the vehicle class, which serves as an example of spaghetti code. This class embodies a common anti-pattern where multiple responsibilities are crowded into a single structure, making it difficult to maintain and extend. As we observe, it contains several methods, each responsible for different functionalities like driving, checking fuel, checking tire pressure, and navigating. This amalgamation creates a tangled web of logic wherein developers may struggle to understand or modify the code. Next, we will analyze the drive method, which is tasked with handling the entire driving mechanism, including engine control and brake checks. Such a broad scope for a single method leads to complexity and hinders testing. The check fuel and check tires methods represent additional responsibilities that further dilute the class's purpose. Finally, the navigate method introduces more intricate logic, complicating matters even further. In refactoring, we would focus on separating these responsibilities into distinct classes or methods, promoting clarity and maintainability. By doing so, we minimize the risks associated with future modifications and improve overall code quality, aligning our designs with best practices. Next, we will explore the issue of duplicated logic through a common example in Java applications. Let's start by examining three classes: fuel checker, tire pressure checker, and engine checker. Each class contains a method that checks a specific aspect of a vehicle fuel level, tire pressure, and engine health, respectively. While each class functions properly, they all share similar conditional logic to evaluate whether their specific parameter is sufficient. This leads to redundancy in the codebase, which can create challenges when updates or bug fixes are necessary. Now let's see how we can improve this situation by creating a utility class called VehicleUtility. This class contains a single static method called checkHealth, designed to encapsulate the common logic for checking various vehicle metrics. By passing the variable type, its value, and a threshold, we can reuse this method across all three classes. Consequently, the check fuel level, check tire pressure, and check engine methods will simply call VehicleUtility checkHealth, significantly reducing code duplication. This approach not only enhances clarity and maintainability, but also promotes better practices by adhering to the dry, don't repeat yourself principle, allowing developers to manage vehicle health checks more effectively. Now let's see how we can implement the blob anti-pattern through a common class design. In our example, we have the vehicle system class, which encompasses a multitude of responsibilities including driving, checking fuel, monitoring tires, and conducting maintenance. This design inevitably creates a God object, making the class unwieldy and challenging to maintain. Each method is tightly coupled within the single class, leading to a violation of the single responsibility principle. This means that any change or addition, such as an update to the driving logic, could introduce errors in other areas like fuel monitoring. To rectify this, we can refactor our code into specialized classes. By doing so, each class becomes focused solely on its designated task. The vehicle class handles driving, the fuel checker class takes care of fuel assessments, while the tire checker class manages tire evaluations, and the maintenance service addresses all maintenance operations. This separation of concerns not only improves the clarity of the architecture, but also enhances maintainability, as developers can now work on individual classes without the risk of inadvertently affecting unrelated functionalities. This approach fosters a cleaner, more organized code base. Now let's take a look at a practical example showcasing the Golden Hammer anti-pattern through a vehicle service class. In this implementation, the class is designed to manage vehicles while relying on a specific database technology that is injected through its constructor. The constructor initializes the database instance variable, which is critical for the addVehicle method's functionality. However, this reliance on a single database solution exemplifies the anti-pattern since it prevents exploration of alternative technologies that may offer better performance or scalability. In this setup, every time a new vehicle needs to be added, the addVehicle method simply calls the save method on the database object. This approach reflects a lack of flexibility and limits the team from adapting to better options that might have emerged after further research. To overcome this anti-pattern, it is essential to encourage open-mindedness in technology selection. Developers should actively experiment with different database solutions and evaluate their potential benefits before committing to one, fostering an environment that respects innovation and adaptability. Next, we'll take a look at a simple class designed as a proof of concept for generating reports. This code snippet exemplifies the lava flow anti-pattern, which is characterized by hastily transitioning unvetted code directly into a production environment. In this class named temporary feature, we have a method generateReport, which is labeled as a rapid solution. This suggests that the intention behind this code was to provide a quick fix or an expedient feature without a thorough evaluation of its robustness or scalability. It serves as a reminder that deploying such experimental code to production can lead to significant issues down the line, such as poor performance and maintenance headaches. To avoid falling into this trap, developers should prioritize a systematic review process for proofs of concept, ensuring that any code intended for production meets established standards. By doing this, we can implement a clear boundary between experimental code and production-ready solutions, ultimately safeguarding the integrity and reliability of our software applications. Now let's take a look at a practical example of the dead-end anti-pattern through a legacy interface. In this case, we have an interface named Vehicle Module that includes several method signatures meant for various system functionalities. Among these, the methods checkEngine and initSystem are valid and in use, while the method initOldRadio is marked with a comment indicating that it is never used, representing obsolete logic. This situation highlights a common issue faced in many software projects where outdated methods clutter an interface, leading to confusion for developers. To address this, we should regularly review our interfaces and remove any dead code. By doing this, we not only clean up the interface but also enhance code readability and maintainability. The goal is to retain only the methods that serve a functional purpose, such as the initMediaSystem method, thereby allowing the code to remain efficient and easy to understand. In essence, pruning unused methods can prevent the accumulation of technical debt and ensure that the interface remains aligned with current system needs. Now let's take a look at the autoprocessor class, which serves as an example of how the input clutch anti-pattern can manifest in a software application. This class contains a method called processOrder, designed to handle the processing of an order by interacting with multiple interconnected services. However, the comment within the method highlights a critical warning. Calls to these services may lead to unforeseen behaviors due to hastily implemented quick fixes. As developers navigate the complexities of interconnected services, one service may malfunction or change behavior over time, prompting the team to whip up temporary solutions. This approach can easily spiral into a tangled web of inconsistencies, where each ad hoc fix further complicates the original issue instead of addressing it. Hence, this highlights the importance of understanding the root causes of problems before applying fixes. To circumvent this anti-pattern, it's essential to maintain a rigorous testing strategy. Doing so ensures that inputs are validated and the expected outputs are determined, thereby preserving the integrity of the overall application and preventing unintended side effects from emerging as a result of independent service fixes. Overall, understanding and recognizing anti-patterns is pivotal in fostering successful application development. They are part of the ongoing design and coding process and can have significant impacts if unchecked. Through education and awareness, we can craft best practices that help us navigate our coding endeavors and improve the health of our software projects. As developers, our objective is to strive for clarity, maintainability, and efficiency. Adapting to these principles while being mindful of potential pitfalls will enhance both our coding efficacy and professional growth in the long run. Remember, in the world of software development, evolution is part of the journey, and embracing it can transform challenges into opportunities. Thank you for joining me in today's exploration of anti-patterns. Let's keep building better software together. In today's lesson, we're diving into the world of identifying common patterns in software development. Understanding and recognizing these patterns is crucial for creating functional, maintainable, and transparent applications. We'll explore ways to spot deviations from our primary objectives and how to align our development practices accordingly. So far, we learned about anti-patterns in software development, which are ineffective practices that can hinder code quality and maintainability. We explored various types of anti-patterns, such as spaghetti code, cut-and-paste programming, and God objects, highlighting their characteristics and implications. Techniques to refactor and mitigate these issues were discussed, emphasizing the importance of clear, manageable code structures. Understanding these anti-patterns equips developers to improve software design and avoid common pitfalls in their projects. Now, we will shift our focus to identifying common patterns that promote efficiency, enhance communication, and streamline project workflows. Now let's see how we can implement the Singleton pattern in Java. In this code, we define a Singleton class that ensures there is only one instance of itself throughout the application. This is achieved through a private static variable called instance, which holds the single instance of the class. The constructor of the Singleton class is marked as private, which prevents other classes from instantiating it directly. Instead, we provide a public static method getInstance that checks if the instance is null. If it is, the method creates a new instance of the Singleton class. If the instance already exists, it simply returns it. This method maintains the global access point for the instance, ensuring controlled accessibility. Additionally, we have a showMessage method that demonstrates functionality by printing a message to the console. This method can be used to verify that our Singleton instance is operational. By implementing this pattern, we maintain a single point of entry for resource management, promoting efficiency and reducing the overhead of creating multiple object instances within our application. This approach leads to more manageable and streamlined code. Now let's take a look at how we can implement the factory method pattern in Java. We begin with an abstract class named vehicle, which declares a method called create. This method is intended to be overridden by concrete subclasses, allowing for specific implementations of different types of vehicles. Next, we define two concrete classes, car and bike, both of which extend the vehicle class. Each of these classes provides its own version of the create method to indicate the specific type of vehicle being created. For instance, when an instance of car is created, it outputs car created, while the bike class returns bike created. To facilitate the creation of these vehicle objects, we introduce the vehicle factory class. This factory class contains a method called getVehicle, which takes a string parameter representing the vehicle type. Based on this input, the factory method determines which vehicle class to instantiate and return. If the input matches car, a new car object is created. If it matches bike, a new bike object is returned. This structure not only encapsulates the object creation process, but also allows for easy expansion in the future. You can simply add more vehicle types without changing the existing code structure, highlighting the flexibility and maintainability that the factory method pattern offers. Now let's implement the observer pattern, which allows us to create a system where multiple observers can react to changes in a subject state. We begin by defining the observer interface, which declares a method update that will be called when the subject experiences a change. This sets the foundation for the observer's behavior. Next, we have a concrete implementation of the observer called concrete_observer. This class has a name attribute and implements the update method to display a message whenever it receives a notification from the subject. This allows each observer to react uniquely based on its internal state. The subject class is crucial as it maintains a list of observers and manages their connection to the events. It has an attach method that allows observers to register themselves for updates. When a change occurs in the subject, the notify observers method is called, which iterates through the list of the attached observers and invokes their update method, passing along any relevant messages. This structure promotes loose coupling and dynamic communication, enhancing the overall responsiveness of the system. By implementing this pattern, we can effectively manage different parts of an application that need to stay in sync with one another without tightly coupling their implementations. Now let's see how we can implement the strategy pattern in Java, a pattern that promotes flexibility by allowing us to define a family of algorithms, encapsulate each one, and make them interchangeable. First, we create a strategy interface that declares a method execute, which accepts two integers and returns an integer result. This interface ensures that different strategies will adhere to a consistent method signature. Next, we implement two concrete strategies, addition strategy and subtraction strategy. Each class provides its own implementation of the execute method, thereby encapsulating the algorithm specific to that strategy, one for performing addition and the other for subtraction. To utilize these strategies, we need a context class that references a strategy object. The context class contains a method setStrategy, which allows us to change the strategy at runtime, thereby dynamically altering the behavior without modifying existing code. The execute strategy method in this class delegates its execution to the currently set strategy. This structure promotes clean, maintainable code and follows the principle of separating algorithmic behavior from the context in which it is executed, enhancing code adaptability and readability. Let's explore the importance of recognizing anti-patterns too, as understanding what not to do is just as critical as knowing best practices. Take the instance of the God object anti-pattern, where a single class tries to encompass too many responsibilities. It can lead to complex and tightly coupled code, which is difficult to maintain. Avoiding this anti-pattern revolves around the single responsibility principle, ensuring each class has a singular purpose. If we find ourselves adding more and more methods to a single class, it might be time to refactor. Consider breaking it down into smaller classes with well-defined responsibilities, which inherently simplifies testing and improves clarity. Now let's take a look at the command pattern implementation. Here we define an interface called command, which includes a method execute. This method acts as a contract for any concrete command we want to create. We then introduce a light class with two core functionalities, turn on and turn off. This class represents the actual receiver of the command, executing the operations. Next, we create two concrete command classes, light-on command and light-off command. Each of these classes holds a reference to the light object, allowing them to call its respective method when the execute method is invoked. This encapsulation enables us to capture a request within an object, paving the way for flexible command handling. Following this, we have the remote control class, which manages command execution. It allows us to set any command and press a button to invoke it without needing to understand how the command operates. This separation of concerns enables us to easily extend or modify commands without altering the client code, a key benefit of the command pattern that supports features like undo and redo functionalities. As we wrap up our exploration of common patterns, let's take a moment to emphasize the importance of recognizing and implementing them. Patterns not only streamline the development process, but also equip you with the tools necessary to create maintainable, scalable, and robust applications. Grasping these concepts will ultimately empower you to become a more effective developer. Remember, each pattern serves a unique purpose, and the key lies in knowing when to apply them appropriately. Don't hesitate to experiment and adapt these patterns to your specific needs. They're there to enhance your development experience. By fostering a culture of pattern recognition within your team, you create a shared language that aids in collaboration and also combats the deviations we discussed at the beginning. Thank you for joining me in this lesson. Keep these patterns in mind as you move forward with your projects, and let's build better software together. Happy coding! In this session, we will explore software architecture patterns, an essential aspect of software design that influences the structure and organization of code. A clear understanding of classes, packages, and module composition is crucial, not only for the application itself, but also for leveraging the power of the Java platform effectively. So far, we have learned about the significance of design patterns in software development as effective solutions to common design challenges. We explored specific patterns such as Singleton, Factory Method, Observer, Strategy, and Command, each contributing to better code structure and maintainability. Techniques for recognizing anti-patterns were also discussed, highlighting the importance of avoiding practices that can lead to complex and unmanageable code. Understanding and applying these patterns is essential for developing robust and scalable applications. Now, we will take a deeper dive into software architecture patterns, examining how they shape our coding practices and lead to better overall project outcomes. Now let's take a look at a practical implementation of the layered architecture pattern. In this example, we define three distinct classes, each representing one of the layers: the data access layer, the business logic layer, and the presentation layer. First, we implement the user repository class as part of the data access layer, responsible for handling data retrieval. This class includes a method, findUserById, which simulates a database query to fetch user information by their ID, returning a new user object with a predefined name. Next, we turn to the userService class, which makes up the business logic layer. This class utilizes an instance of user repository to access data. Its getUser method calls the findUserById method from user repository, effectively encapsulating the business logic of obtaining user details without exposing the data retrieval logic directly. Finally, the userController class represents the presentation layer. It interacts with the user service to manage user interactions. The displayUser method fetches a user by ID through the user service and prints the user's name to the console. This clear structure allows each layer to collaborate while maintaining separation of concerns, enabling modifications within one layer without affecting the others. Now let's see how we can implement a simple product service in our microservices architecture. The product class is designed to represent a product with unique attributes, an identification number, and a name. It features a constructor to initialize these attributes and a method to retrieve the product name. Next, we will create the product service class, which acts as a manager for multiple product instances. This class maintains a list of products using an array list, enabling dynamic management of the products stored. The addProduct method allows new products to be added to this list, ensuring that the product service can uphold its responsibility for managing the product catalog effectively. Additionally, the getAllProducts method provides a way to retrieve the entire list of products, making it easy for other services or components to access the catalog. In a microservices environment, the product service can be exposed through HTTP APIs, allowing different parts of the e-commerce application to interact seamlessly, such as querying for product details or adding new products. This modular approach not only enhances the service's scalability, but also promotes independence and maintainability within the overall architecture. Now let's take a look at how we implement the event-driven architecture in our e-commerce application. We begin by defining an interface called event, which includes a method to retrieve the event name. This interface allows us to create different types of events without coupling the event handling logic to specific event types. Next, we implement a class called OrderPlacedEvent, which extends the event interface. This class holds the ordered attribute, representing the identifier of an order placed by a customer. The getName method constructs a descriptive string that indicates an order has been placed, incorporating the order ID. Now let's move on to the EventPublisher class, which plays a critical role in our architecture as it manages the registration of event listeners and the publishing of events. It contains a list of listeners and a subscribe method that allows other components to register their interest in specific events. The publish method is responsible for notifying all registered listeners when an event occurs, facilitating asynchronous communication. Finally, we define the order service, which implements the event listener interface. This class allows the service to respond to incoming events by providing its own onEvent method to handle the received event gracefully, demonstrating how various components can remain loosely coupled while still interacting effectively. Now let's implement a simple serverless function to handle payments in Java. In this example, we define a class called Payment Handler, which encapsulates the functionality related to processing payments. The primary method within this class is processPayment, which takes a string parameter named payment details. This method simulates the payment processing logic by returning a message that indicates the payment has been processed for the provided details. By structuring our function in this way, we harness the advantages of serverless architecture, allowing it to dynamically respond to events like payment requests without being tied to a specific server. This separation of concerns means that developers can focus solely on the application logic, improving maintainability and scalability. Once deployed on a cloud function platform such as AWS Lambda, this function can be easily triggered by various events through an API gateway. This capability ensures that our payment handling is efficient and can scale rapidly based on demand, all while minimizing infrastructure management responsibilities. Understanding these architecture patterns is a valuable investment in your software development skills. Each pattern serves its unique purpose and can lead to organizing your code efficiently, enhancing maintainability and scalability. Selecting the appropriate architecture for your application context helps manage complexity, allowing for progressive development and easier troubleshooting. Throughout this session, we explored various architecture patterns, including layered architecture, microservices architecture, event-driven architecture, and serverless architecture. Each model offers distinct advantages and should be leveraged according to the specific requirements of your software project. In conclusion, architecture patterns continue to evolve, reflecting the growing demands of today's software development landscape. By gaining familiarity with these patterns, you can make informed decisions on structuring your projects and ultimately create better software. Each pattern's characteristics should guide you in evaluating which best fits your development needs. Thank you for joining me in this exploration of software architecture patterns. As you dive into your projects, remember to consider how your architecture can influence the overall quality, performance, and maintainability of your application. Happy coding! Technical debt is an interesting concept because it requires the context of the software application and its goal in order to understand it. In the fast-paced world of software development, we often make trade-offs between quick solutions and long-term sustainability. This is akin to taking out a loan. While it may offer immediate benefits, it comes with future obligations that need to be addressed. By the end of this discussion, you will have a comprehensive understanding of technical debt, its implications, strategies to manage it, and how to write code that minimizes its accumulation. So far, we learned about various software architecture patterns, including layered architecture, microservices architecture, event-driven architecture, and serverless architecture. Each pattern provides unique advantages in managing complexity, enhancing scalability, and improving maintainability in software development. We discussed how these architectures facilitate clean separation of concerns and allow for independent development and deployment of components. Understanding and utilizing these patterns is essential for creating robust and effective software applications. Now, we will talk about addressing technical debt and how it impacts our development process. Now let's take a look at the discount calculator class, which demonstrates a straightforward approach to applying a discount to an original price. This class has a method named calculateFinalPrice, which takes the original price as an input and computes the final price after deducting a hard-coded discount of 10%. While this implementation is functional, it introduces technical debt, as any change to the discount value would require modifications directly in the code, leading to maintenance challenges. Next, we will enhance this design by introducing flexibility. Instead of hard-coding the discount, we can pass it as a parameter to the constructor, allowing different discount values without altering the code logic. This approach promotes adaptability, making it easier to manage various discount strategies in the future. By implementing this change, we not only improve the maintainability of our code but also reduce the potential for errors, contributing to a cleaner and more sustainable codebase. Ultimately, this illustrates how thoughtful design choices can minimize technical debt while promoting effective software development practices. Now let's see how we can implement a more flexible approach to our discount calculation to minimize technical debt. In this revised version of the discount calculator class, we introduce a constructor that accepts a discount value as a parameter. This design allows users to specify different discount rates without altering the core logic of the calculator, enhancing the adaptability of our application. The discount parameter is stored as a private final variable, ensuring that its value remains consistent throughout the lifetime of each instance of the class. By doing this, we decouple the discount value from the calculation process, making the class more maintainable and reducing the likelihood of introducing errors because we no longer rely on hard-coded values. Next, when we call the method to calculate the final price, we can easily pass a new discount value to the constructor. This modification supports the implementation of various discount strategies without requiring changes in the code each time a discount value needs updating. Such an approach not only streamlines our code but also lays the groundwork for scalability, ultimately leading to reduced technical debt and increased developer efficiency. Now let's see how we can implement a simple scoring system to assess the technical debt of our code. We will create a class called CodeQualityScore that encapsulates the logic for calculating a score based on three key factors: complexity, lines of code, and bug count. In the constructor of this class, we define the properties complexity, lines of code, and bug count, which represent the three metrics we'll evaluate. By initializing these values upon instantiation, we equip our object with the necessary data to perform the scoring effectively. Now let's focus on the CalculateScore method, which is pivotal to our scoring system. This method computes the total score by adding the complexity directly to a weighted score derived from the lines of code and bug count. We divide the lines of code by 10 to scale this metric down, while we multiply the bug count by 2 to emphasize its impact on technical debt. The resulting score gives us a clear indication of how critical it is to refactor that particular piece of code. Ultimately, a higher score signals that the code requires attention and potential refactoring to lower overall technical debt. Now let's take a look at how we can enhance our discount calculation functionality by implementing the OfferCalculator class. This class introduces a flexible approach to managing discounts, as it allows the discount rate to be passed as a parameter during instantiation. This design improves the code's adaptability. If the discount rate needs to change, we can simply create a new instance of OfferCalculator with the new discount value, rather than modifying the core logic of our code. Within the class, we have a private final variable that stores the discount rate. This ensures that once the discount is set for an instance, it cannot be altered, maintaining consistency throughout the object's lifecycle. The applyOffer method is responsible for calculating the final price by subtracting the discount from the original price. By utilizing this method, we encapsulate the discount logic, making it reusable and easier to manage. This structure not only reduces potential technical debt by avoiding hard-coded values, but also enhances clarity in the code, indicating that the class's purpose is to handle offers effectively. Now let's take a look at how we can implement unit tests for our OfferCalculator class using JUnit, a popular testing framework for Java. In the OfferCalculator test class, we define a test method called testApplyOffer that ensures our applyOffer function works correctly. This method begins by creating an instance of OfferCalculator, passing a discount rate of 10% to it. Next, we call the applyOffer method with an original price of 100, which should return the final price after applying the discount. We then utilize the assert=equals assertion to verify that the calculated final price is indeed 90, allowing for a small margin of error. The assertion checks if the actual result matches our expected outcome, thus confirming that the method behaves as intended. Implementing this test provides a safety net, so if future modifications to the code inadvertently introduce errors, we will be alerted through failing tests. Maintaining a suite of automated tests like this encourages confident refactoring and helps manage technical debt more effectively in the software development process. In addition to automated testing, you can utilize static analysis tools that help spot potential sources of technical debt before they escalate. Tools like SonarQuiber or Cristal analyze your codebase for complex structures, duplicate code, or non-adherence to your coding standards. Integrating these tools into your CI/CD pipeline can automate the detection of technical debt, providing feedback as part of the build process. Imagine your build process running, and suddenly it flags complexity issues in your discount calculator code. Instead of finding out later during maintenance, this immediate feedback allows you to rectify it while the context remains fresh. Now let's take a look at the OfferCalculator class, which serves as a powerful tool for applying discounts to prices. This class is designed with a clear purpose and structured documentation, ensuring that anyone interacting with it can easily understand its functionality. The constructor of the OfferCalculator accepts a discount parameter, representing the discount rate between 0 and 1. This approach provides flexibility by allowing you to easily modify the discount applied to the price without changing the core logic of the class. Next, we will explore the applyOffer method, which takes the original price as input and calculates the final price after applying the specified discount. By multiplying the original price by the discount, the method effectively determines the discount amount and subtracts it from the original price, returning the final payable amount. This clear design not only enhances maintainability, but also reduces the technical debt associated with hard-coding values. As we progress through our tutorial, it's vital to appreciate how such structured and well-documented code contributes to more manageable and adaptable software design. Finally, addressing technical debt is an ongoing process rather than a one-time fix. Regular assessments, team engagement, and adapting best practices will ensure your projects remain healthy and your codebase manageable. Technical debt is not inherently bad, it allows you to move quickly, but being strategic about it can enhance your productivity in the long run. Continuously monitor your code, delegate time to tackle debts systematically, and foster communication within your team. With the right practices, you can minimize technical debt while ensuring your software remains robust, maintainable, and ready for the challenges of tomorrow. By embracing these strategies, you are not just reducing technical debt, you are leveraging your codebase for future enhancements, making it easier to integrate new features and creating a more enjoyable environment for yourself and your team. Software development is a journey, and by being cognizant of technical debt, you're setting yourself up for success every step of the way.